Oh, there it is.
Great. Good morning. It's my great pleasure to introduce our next keynote speaker for the day, Carolyn Triple from Stanford University. Carolyn is an architect, a computer architect, whose research focus is on applying formal methods and automated reasoning to improving the assurance of processor security, reliability, and correctness. And today, she is going to be telling us about hardware-software contracts for high assurance with applications to side-channel security. Carolyn.
Great. Yeah, thanks a lot for the introduction, and thanks a lot for having me. I was really honored to receive the invitation to come speak to everyone here, and I'm excited to tell you about some of the work we've been doing on designing and verifying hardware-software contracts or hardware implementations of hardware-software contracts. In other words, hardware-software interfaces that support the development of high-assurance software. And in general, by high-assurance software, what I mean is software that can support the correctness, security, and reliability guarantees, or requirements, rather, of programs. And for the most part, in this particular talk, I'm going to focus on a specific instance of this problem where high-assurance software refers to software that has been secured against hardware side-channel attacks. So to jump right into it, what is a hardware side-channel attack? So in general, these attacks involve a victim program that is running on some vulnerable hardware implementation, and it leaks its secret data to an attacker who can measure physical aspects of either its own or the victim's execution. So physical aspects can be things like program execution time, power dissipation, resource contention, and more. And so to be a little bit more precise, there's a nice telecommunications analogy that has emerged in the literature for defining hardware side-channel attacks. And it describes these attacks as featuring a so-called transmitter instruction, which is a leaky instruction in the victim program, that modulates a channel, or a channel is a hardware resource, in an operand-dependent manner, and a receiver, which is the attacker, that observes this channel modulation in order to infer the transmitter's operand value. And so in other words, transmitters are instructions that leak one or more unsafe operands by creating observable operand-dependent hardware resource usage. And so which instructions are transmitters and which of their operands are considered unsafe is very specific to a particular hardware implementation. But loads, like the one on this slide here, are very commonly assumed to be transmitters with unsafe address operands. And this is because loads often modulate data cache lines in hardware as a function of their address operands by using them as an index into these caches to decide which region of the cache to update or access. And so a receiver that's running on the same hardware as the load transmitter, say, can observe these sort of data cache line modulations as hits or misses with different access latencies for its own memory accesses that happen to map to the same cache line as the victim transmitters, and thereby, indirectly infer the load transmitter's address value. So, hardware side-channel attacks have been around for a long time, since the early 2000s at least, and the gold standard approach for protecting software from hardware side-channel attacks is something called the constant-time programming defense. And this defense relies on the availability of what I'll call a hardware-software leakage contract, or constant time leakage contract specifically. And this is a hardware-software interface that enumerates a specific hardware implementation's transmitter unsafe operand pairs. So an example is like what you see here on the slide. And these constant time leakage contracts typically include memory operations and their address operands. This is due to the presence of data cache optimizations like I just illustrated on the last slide. Conditional branches and their operands are also commonly included in these lists due to a variety of optimizations that can leak the program counter of executing instructions, including instruction caches. And then there's usually a variety of variable time arithmetic operations that you'll see on these constant time leakage contracts. Division is one common example, say to different execution paths the division might take with different execution latencies depending on its operand value, say a fast path for division by 0. All of these specific details I'm highlighting about, how a transmitter might leak its unsafe operands, those are irrelevant. And all that these constant time leakage contracts include is, this instruction you should consider as being leaky with respect to some operand value. So if you have one of these constant time leakage contracts, then what the constant time programming defense requires is that you write your programs to ensure that secret dependent data never reaches the unsafe operand of a transmitter instruction. And doing so ensures that the attacker observable executions of a program P, say that's running on some particular hardware implementation denoted by this little icon here, all attacker observable executions of that program on that hardware are indistinguishable as a function of the program's secret inputs, which is conveyed by this non-interference property on the bottom right-hand side of the slide. So as evidence of the importance of constant time programming, constant time leakage contracts have been recently adopted by industry over the last few years. And the slight difference is instead of enumerating transmitter unsafe operand pairs like I will in the slides, they enumerate non-transmitter safe operand pairs, but for all intents and purposes, we can think of it as the same thing. So to give a couple examples, ARM and Intel have these mode-enabled leakage contracts. So you put the processor into a particular mode, and then it's going to temporarily disable hardware optimizations that would leak instructions safe operands with usually some performance penalty associated with that. And then RISC-V is another example of an architecture that has dedicated instructions whose safe operands are always guaranteed to be safe and not leak via hardware side channels, so no specific mode-enabled implementation there. And so this constant time programming was long thought to be sufficient for securing constant time code against hardware side channel attacks, and as a result, it's frequently applied to cryptographic code. And one concrete example is on this slide here. There's this Salsa 20 stream cipher excerpt from the open source libsodium cryptographic library. And I've highlighted the secret dependent data in yellow in the program. And this program is constant time, so it's been written so that no secret data ever reaches the unsafe operand of a transmitter. However, this is the case in any architectural or software visible execution of the program, which traditionally are the only executions that software developers or compiler writers are expected to consider. But what happens when this program executes transiently? Like, can secrets reach the unsafe operands of transmitters in the transient executions of this program? Where a transient execution refers to the partial execution of instructions by hardware, so this is behind software's back, along wrong code paths that are eventually squashed before they've had a chance to update software visible state, aka architectural state. So to see how this, transient execution that hardware is, realizing under the covers, to see how that can cause a problem, we'll zoom into this libsodium example. And we can take a look at this call to load 32, which returns the first 32 bits of the secret key. And so this is what this load 32 function compiles down to in x86 assembly. So it's just a load of the secret and then a return. And so architecturally, this code is fine. So it doesn't, the secret doesn't leak. The caller is simply just, storing the returned value to the stack. However, what can happen at runtime of this program on hardware is hardware could mispredict the return address of this function at runtime along a wrong code path to a transient transmitter that leaks the secret. And so even though this transient transmitter, it's not going to architecturally commit and update any software visible state, it can still modulate hardware side channels in the design, which are inherently not architectural state. They're usually microarchitectural state, or state that's invisible to software. And so, for example, this load transmitter could still leak its address operand by modulating or perturbing a data cache line as a function of that secret-dependent address, and this can be detected by an attacker or receiver later on. So a hardware side channel attack like this one, where the transmitter instruction, the leaky instruction, is transient due to a hardware misprediction, this is called a Spectre attack. And there are many common sources of hardware mispredictions on modern processors, with these 5 being particularly common and well studied. And the misprediction in this example is an instance of return address misprediction, or RSB for short. The acronyms are a little counterintuitive since they correspond to the hardware structures that are usually responsible for creating these sorts of predictions, but I'll usually just reference the acronyms throughout the talk. So I'm going to revisit this example a little bit later, but popping up a level. In general, any program that runs with secrets in architectural state, whether it's architectural registers or memory, is vulnerable to Spectre. And this figure decomposes all Spectre vulnerable code into a hierarchy of 4 increasingly broad classes, where the first class, I'll refer to as this architectural or arch code, which contains all code that does not hold secrets in architectural registers. So some common examples of code from this code class would be, JavaScript or WebAssembly running in a browser, or eBPF bytecode that's running in a kernel. And all of the remaining code classes besides this one can hold secrets in registers when they execute. So I'm going to skip to this constant time code class first, the CT code class. So this is code that does not architecturally leak or transmit secrets by passing them to transmitters. And many cryptographic primitives fall into this category, like the libsodium example we just saw. This static constant time code that I'll single out as a special subclass of constant time code that architecturally only places secret data in registers that can be statically typed as secret. And so examples of this code class would be explicitly typed cryptographic code, maybe written in the FACT or CT-WASM languages, or untyped cryptographic code for which a valid typing is known to exist. So this kind of code, for example, cannot feature cryptographic declassification of secrets. And then lastly, there's this unrestricted code class that, this is code that might architecturally access and leak secrets. Non-constant time cryptographic routines or much of the Linux kernel will fit into this category, but these Spectre attacks can make the secret data that's architecturally leaked by these programs much more easily accessible than if you were to rely on the program's architectural executions alone. So I'm going to talk about, some ways in which we can defend comprehensively programs from Spectre attacks. But if we want to do that, in fact, if we want to defend programs from hardware side channel attacks in general, we really do require cooperation between hardware and software. And so in this talk, I'm going to decompose this cooperation into 5 components that characterize whether or not some hardware side channel defense, or Spectre defense, can secure a particular program, where the first 2 components are implemented by hardware, and these first 2 components characterize hardware's baseline vulnerability to hardware side channel attacks. So this leakage contract component is what characterizes the transmitters on a hardware implementation, like the constant time leakage contract we saw. And this execution contract component characterizes the possibly transient control and data flow semantics of the hardware. The next 2 components, this protection set and protection mechanism, they collectively characterize a hardware side channel defense that's been layered on top of some baseline implementation, and these can be implemented in hardware or software or some combination of both. And this protection set I'm going to use to define what software visible state at each program point a defense promises to protect from leaking. And then I'm going to use this protection mechanism component to define how a defense is protecting that protection set from leaking, how it's enforcing its protection set. And then the last piece here, before I get into some more specific examples, is this secret set component, which is a property of software, and it defines what architectural state or software visible state at each program point may contain secret program data. So it's basically identifying the class of programs from the previous slide that a defense can target. And the last little piece here is, whenever a component is implemented in hardware, so I have this sort of, hardware notation here, it becomes a hardware-software contract that software relies on hardware to implement correctly. Okay, so I have three main technical parts to this talk. So the part 1 and part 2, I'm going to talk about some of our work on designing new hardware-software contracts that support the design of new Spectre defenses. And then in part 3, I'm going to talk about some of our work on designing what I'll call a meta leakage contract that captures all features of, I'll say, nearly all leakage contracts in use by hardware side channel defenses today, of which there are many. And in doing so, in designing this meta leakage contract, we were able to design a unified formal verification procedure for automatically confirming that hardware adheres to, any of the leakage contracts from the literature, or find bugs in cases where it does not. Okay, so I'm going to start with Cerberus, which was the first defense that is deployable on real hardware today for fully securing a slight restriction of constant time code, static constant time code in particular, against Spectre attacks involving the 5 common types of speculation from a few slides ago. And so this slight restriction of static constant time code, in addition to having this statically secrecy typable property, it also avoids passing secrets by value, so it only passes secrets by reference. And so Cerberus assumes that the hardware implements a very standard constant time leakage contract that just enumerates these transmitter unsafe operand pairs, along with a new execution contract that we proposed called ASP for Abstract Speculative Processor. And as a software defense, Cerberus implements both its protection set and its protection mechanism in software, and each of these 3 novel components is designed to address a specific challenge that is faced by all software defenses against Spectre attacks. So I'll talk about those next. So starting with this execution contract challenge, which is that compile time analysis of a program's transient control and data flow graph is intractable by default. So we solve both aspects of this challenge, but I'm going to focus mostly on the control flow aspect. And the problem is that by default, hardware can cause a program to exhibit unconstrained transient control flow. So for example, return instructions can transiently in hardware return to any instruction in the program, including ones that are hidden within compiled instructions due to variable length instruction encodings in some instruction sets like x86, for example. Further, we have function calls that can transiently jump to any instruction, including hidden ones again. And the result is this messy transient control flow graph that I don't think anyone would want to analyze at compile time. And so our solution to this problem was based on this observation that we had and others had, which is that control flow integrity extensions, or CFI extensions in modern instruction sets, an example is this Intel control flow enforcement technology. These are hardware extensions that enable software to judiciously constrain its software visible or architectural control flow at compile time. And the observation was that if software could similarly judiciously constrain its transient control flow at compile time, it could do so just enough so that the transient control flow could be reasoned about by compiler analyses. And so we had some discussions with collaborators at Intel, and we found that CET actually does have some useful transient semantics on Intel efficiency core implementation specifically. So, one line of Intel hardware does actually have nice transient semantics that we can use for this Intel control flow enforcement technology, and they've now clarified this in some new documentation in response to this work. So what are these useful transient semantics, and how do they help resolve our execution contract challenge? So to start, if we enable this Intel CET's indirect branch tracking feature, we can ensure that calls and jumps only transiently jump to end branch instructions, which are special dedicated instructions provided as part of this hardware extension. We can ensure that basically this forward edge indirect branch control flow will only ever jump to end branch instructions in the program. So it could jump to wrong end branch instructions, but it's guaranteed to only jump to an end branch instruction, and so our Cerberus defense inserts these instructions at each function entry point. Next is CET has this shadow stack feature, which combined with another non-CET feature that's called this RRSBA disable speculation control. Basically, it just prevents return address predictions from being serviced by the indirect branch predictor on return stack buffer underfills. So together, these two features can ensure that returns only return to call sites. And so Cerberus enables all three of these features. So, basically what we've done here is that we've significantly constrained the transient control flow graph of this program. The CET and, these three mechanisms here are not a Spectre defense in and of themselves, since, you can see even after we've enabled them, we still have this transient leakage of our secret that's possible in this program, but now the secret can only leak along one transient control flow path instead of a very large number of paths. So this, you don't have to look at all the details here, but this ASP execution contract we define is, just an operational model that formalizes a program's sequential and transient control and data flow semantics on hardware that implements all three of the mechanisms we just discussed for constraining a program's transient control flow, along with speculation fences and some other features that allow us to constrain a program's transient data flow. I'm going to skip a lot of details here, but at a high level, this ASP model constrains data flow speculation that arises when, so essentially it constrains data flow speculation to only permit loads to return values from wrong stores to the same address, which is something that can happen in modern hardware today. So a load might guess the address that it's supposed to access because address computation takes some time in a processor. And so we permit loads to get wrong data from stale stores to the same address, but not stores to different addresses, which is another behavior that can happen on some hardware. And then the speculation fences restriction. So speculation fences are sort of a new term for fences that already existed in certain instruction sets, which are basically serializing instructions that require execution of all instructions before the fence to complete before the fence can execute. So they basically have the effect of terminating any ongoing transient execution before the fence can execute. So we have this model that describes all of these. We've been able to, with this model, restrict the control and data flow graph, transient control and data flow graph of a program at runtime on hardware just enough that we can defend the program from Spectre attacks. But the next thing we need to do is figure out how to do that. So, what data should we be protecting from transiently leaking at each program point to ensure that all secret data in static constant time code, or a slight restriction of it, is protected from transiently leaking. So prior hardware defenses in particular had prevented the outputs of these so-called access instructions from transiently leaking. So they blamed Spectre leakage of secrets in programs on access instructions, which they defined as instructions that load secrets into registers, load potential secrets into registers. But if one of these access instructions loads a secret into a secretly typed output register in a static constant time program, which is what an architectural or sequential access instruction will do, like this one that did not execute transiently, the static constant time program is already going to protect that secretly typed output register, say, from leaking. And so access instructions aren't quite precise enough. So instead, we propose to root cause Spectre leakage of secrets in programs to these instructions we call taint primitives. And they're instructions that can cause a publicly typed output register in a static constant time program to transiently hold secret data. An example, example of one of these taint primitives is a return instruction, like this one in our example, because at its transient target, a register, which you can think of as kind of an implicit output register of the return, could be publicly typed. but hold a secret value. So an example is, this in static constant time code, we have a requirement that all unsafe operands of transmitters be publicly typed. And so if this return returns to a location where there's some secret left over in this register RCX, but the location that it returned to expects public data there, we have this security type violation, we call it, introduced by a taint primitive instruction. And the interesting thing is that we can prove, and we did in the paper, that there are, first of all, taint primitives are necessary for spectral leakage of secrets in programs, and then secondly, that there are only 4 types of instructions that can serve as taint primitives in our static constant time code when it runs on hardware that upholds this ASP execution contract. And so these are the 4 types of instructions that I can go through briefly. So first, we have these non-constant address loads. So these are loads whose addresses, are dynamically computed from data at runtime, and so they could transiently point out of bounds and read out of bounds secret data into their publicly typed output register. Second, we have non-constant address stores. So these stores can transiently, say, write secret data to an out-of-bounds memory location that's later read by a load that has a public output register. And then third, we have uninitialized stack loads. So these are loads that can actually transiently skip over initialization stores due to hardware data flow mispredictions that I briefly mentioned, and they can read stale data from a stale stack frame into a stale secret data from a stale stack frame into a public output register. And then the last one is we have calls and returns, like the example we just looked at, which can be mispredicted to a wrong target that expects, a public argument in a register that holds a stale secret value from the caller or callee. So, we have this constrained set of taint primitives, and the nice thing about this is it enables us to design a novel software protection mechanism for specter defenses that's based on either eliminating one of these taint primitives through code transformations or preventing it from passing its outputs to transmitters' unsafe operands. And we do this latter part using speculation fences. So Cerberus implements this protection mechanism. So to block, and it does so to block specter attacks exploiting any combination of these 5 speculation types from the beginning of the talk. It's implemented as 3 LLVM compiler passes. So we have this function private stacks pass, which assigns distinct physical stacks to each function in order to eliminate taint primitives that arise due to stack sharing. We have this register cleaning pass that zeroes out calls and returns to eliminate interprocedural taint primitives. So this is like the return and the running example. And then we have this fence insertion pass. So this pass inserts a minimal number of speculation fences to eliminate any taint primitives that can't be eliminated by the former 2 passes. And so basically what it does is it identifies a bunch of source sink pairs where the source is a taint primitive and the sink is some dependent transmitter along some transient control flow path in the program. And we formulate fence insertion as a minimum directed multi-cut problem, prioritizing placing fences outside of loops when we can in order to cut all paths from sources to sinks. And the effect that these speculation fences have is these taint primitives will no longer be able to transiently pass any privacy type violating output registers into the unsafe operands of transmitter instructions. So that was Cerberus. There's some pros and cons. So the pro is that it is deployable today on real hardware. It's comprehensive for hardware that upholds some constant time leakage contract, like ARM, Intel, or RISC-V hardware, and this ASP execution contract. So this is the biggest caveat. So, from talking with Intel engineers, we think there are some Intel microarchitectures that do uphold this ASP execution contract along with, featuring a constant time contract, although this is sort of yet to be formally verified on real implementations. But based on discussions, we think it's comprehensive for some hardware. And it's actually reasonably performant. So for 2 different classes of cryptographic workloads we looked at, we had 7% and 21% average overhead for these different cryptographic routines. The cons are that it's not comprehensive for most hardware. So, hardware that doesn't uphold these two restrictions, Cerberus won't be comprehensive for. It could still help you a little bit, but we're interested really in comprehensive defenses. It's also not programmer transparent, and we can debate, the degree to which we want to give up on programmer transparency, because I think it is worth doing so. But we do have this restriction that code cannot pass secret data by value. It can only pass secret data by reference, and this is really a performance decision. So we could handle code that passes secrets by value, but we'd have to insert many more of these fence instructions into the program, which are what contribute to Cerberus's overhead. So it's, as you maybe noted here already, it's not performant for general purpose code. So in cryptographic code, we generally have this nice looping structure. We're looping over some buffer and performing some computations, and we can strategically place these heavyweight fences outside of loops, but we can't do so for general purpose code. So to resolve these limitations, we very recently designed Protean, which is the first specter defense that is altogether comprehensive. So again, by comprehensive, just to clarify, I mean it's a defense that blocks leakage due to all transmitter and speculation types, known or unknown. It is programmer transparent, meaning no source code modifications are required, although maybe we could benefit from some. And then it is also programmable, so it's capable of tailoring its protections to the needs of any individual program. Protean assumes that hardware implements a leakage contract that's a little bit more detailed than the constant time leakage contract we've been looking at, as well as an execution contract that's able to capture all flavors of hardware mispredictions, all flavors of transient execution due to hardware predictions, whether they're known or unknown today. And I'm going to skip the details of these because we borrowed them from prior work. Unlike Cerberus, which was a software defense, Protean is a hardware software defense, where we have software define the defense's protection set and communicate it to hardware to track, and hardware implements the defense's protection mechanism. And so both of these new components are designed to address specific challenges that are faced by all prior comprehensive programmer transparent defenses from the literature, and I'll talk about those now. So this protection set challenge refers to our observation that existing comprehensive and programmer transparent specter defenses, which are shown in the row labels here on the left-hand side of the slide, they actually all happen to be hardware defenses as well, interestingly. So they only target one specific class of specter vulnerable code. And by targeting a class of code, I mean that the defense is tailored to performantly secure it. So for example, if you look in the middle here at SPT, which is one of these hardware side channel defenses that is somewhat recent, SPT is targeting. It's designed to target constant time code. And what this means is that it can secure code classes that it subsumes. Typically, it will do so with less performance overhead, but could be comparable. And then it's unable to secure any code classes that are more permissive than it, that handle secrets in a more permissive way from that hierarchy that I showed at the beginning. And so the problem with this is that if you wanted to secure a multi-class program, of which there are many important ones, like web servers and operating system kernels, you need to pick the most conservative, at least today, you need to pick the most conservative and slow defense that targets the program's most broadest code class. And so the numbers here that you see, these are the lowest runtime overheads that were achieved for a specific, for different class-specific workloads and a multi-class Nginx HTTPS web server when they're running on hardware that implements a particular defense that's capable of fully securing them, and this is all relative to an insecure baseline hardware implementation. Okay. So, why is it that these defenses can only target one code class? The reason is that they all feature these fixed hardware-defined protection sets. And these protection sets, again, a protection set is defining at each architectural step of the program's execution what data the defense is going to protect from speculatively leaking, in this case. Because they've defined these fixed protection sets in hardware, they can't be adapted to meet software's needs. And so our solution to this, protean solution to this protection set challenge is what we call the POPL'26 architectural extension. And it enables software to dynamically define and update as it executes a hardware-tracked architectural protection set. And so specifically, this POPL'26 extension, it provides a single bit instruction prefix, so one bit you can stick in front of instructions, that enables adding architectural registers and memory bytes to the protection set whenever they're produced or written. And then we can also, and you do this by POP prefixing an instruction. And then you can also remove architectural registers and memory bytes from the protection set when they're read or written by unprot prefixing an instruction. So currently, this POPL'26 doesn't support adding registers and memory bytes to the protection set when they're read. This is because they may have already leaked in the past, but I actually think there's some reasons to enable this feature sort of strategically in the future. One other thing too here is I drew these, explicit unprot prefixes, just to go back. So I drew these explicit unprot prefixes, but in POPL'26 binaries, the presence or absence of a prot prefix denotes, or the absence of a prot prefix denotes an implicit unprot prefix. So I'll just draw it this way. Okay, so, proteans, solution to the protection set challenge, one piece of it is this extra instruction prefix. Another piece of it is that we implemented this POPL'26 compiler, which helps us achieve this goal we had, at least initially, of programmer transparency. Hardware people in particular don't like the idea of code having to be rewritten, although I think there are, again, nice reasons to do that. And so this POPL'26 compiler, what it does is it can automatically program our POPL'26 protection set, so automatically add prot prefixes, if you will, to the different instructions in your program for any function or component given just its code class. And it just uses very simple register level data flow analyses to do this. So the pass for Arch code is the simplest. So it's just a no-op pass, so this pass does nothing. And it's nice because this code is usually untrusted. This is code that is not allowed to access secret data architecturally, so every instruction is implicitly unprot prefixed. Then we have this static constant time code pass, so it initializes all registers to secret types and applies secrecy typing rules, including that transmitters' unsafe operands must be publicly typed, and it resolves type errors by typing data as public. The constant time pass, so it can perform less unprotection than the static constant time code pass, so it can only unprotect registers that were passed to transmitters in all past control flow paths, or will be passed to transmitters' unsafe operands in all future control flow paths. So this past leaked or bound to leaked data in your program is what this pass will unprotect. And then for unrestricted code, we can do the least here from like a programmer transparent point of view. So all data is protected except for the stack pointer, constant initialized registers, and then any data that is solely computed from both, either. So, POPL'26 basically is telling hardware at each program point the architectural state that should be protected from transiently leaking, but the protection mechanism challenge involves figuring out how to protect it. And so to solve this challenge, we proved that there are two ways in which this prot-labeled data can transiently leak on arbitrary, speculative, out-of-order hardware. So one way is you could, the hardware could directly try and pass this prot-labeled data to the unsafe operand of a transient transmitter, and that's what's happening here. So we've added this register. We track protections at the granularity of full registers, so we've added this register RCX to the protection set, and here, we've jumped to this transient instruction that has directly passed this prot-labeled data to a transmitter's unsafe operand. And then there's this other type of leakage where we could have an instruction that, say, transiently unprotects some data, like this first add, and then that transiently unprotected data is passed to the unsafe operand of a transmitter. And so Protean provides two different hardware protection mechanisms with different trade-offs, different performance complexity trade-offs. They can both block these two types of leakage. They do it in slightly different ways. So one's called prot delay and the other's called prot track. And so to block this type 1 leakage, both defense alternatives are the same. So they both just stall transient transmitters whose unsafe operands are protected, like this first load, until it's guaranteed that the processor will commit them. And then to block this type 2 leakage, delay has a simpler hardware implementation, so it indiscriminately stalls all instructions that depend on data that was unprotected by some transient instruction until it's guaranteed that that unprotecting instruction will commit by hardware. And then PROTRACK has more complex hardware in order to stall only transmitters whose unsafe operands depend on data that was unprotected by transient instructions. And so to block this type 2 leakage, basically in this example, delay will stall both of these instructions until it's sure this instruction will commit, and the PROTRACK mechanism will only stall this latter instruction. So it gets a little bit better for performance. I'm going to skip the details of the hardware implementations. We build them by extending some prior work, essentially to be able to handle these programmable protection sets. So coming back to this slide from earlier, this has some different performance overheads for class-specific and multi-class benchmarks that are running on secure versus insecure hardware. And the takeaway is that Protean offers better performance than all state-of-the-art class-specific defenses on all workloads. Notably, this unrestricted class, which I mentioned earlier, it does perform better than the baseline. It's not exactly low overhead, but I'll talk about how we can improve this in future work. This was the code class where we could make very little assumptions based on just the code class about what data is public. Another interesting thing actually is that the performance overhead is actually not so different between the simple hardware implementation and the more complex, and I think cautiously optimistic that we could actually get the simple hardware implementation to be zero overhead with the right coordination with software. Okay, so I wanted to just touch on one last thing before I wrap up, which is, I've been talking about designing hardware-software contracts to just support Spectre defenses. We've also looked at designing hardware-software contracts to help us design verification procedures. And one verification procedure we built based on this idea was called SynthLC, and it gives us a way to verify automatically hardware adherence to virtually any of the leakage contracts in use by state-of-the-art hardware side channel defenses today. Just a quick reminder, these leakage contracts, they characterize the transmitters of the hardware implementation. So what are the leaky instructions, and potentially some more information about how they leak their operands. So we observed in this verification work that when transmitters modulate these channels or hardware resources as a function of their unsafe operands, they actually create operand-dependent execution path variability for one or more instructions. And it's this execution path variability for instructions, like that manifest, say, as a fast or slow path, that what a attacker or receiver is ultimately measuring or detecting to infer these transmitter operand values. So example is this is a very typical program pattern in a classic hardware side channel attack. We have this transmit instruction and a secret being passed to its unsafe operand. A concrete instance of this example is maybe I have a multiply instruction on hardware that implements this zero skip multiply optimization that we can describe with this little function here. And it basically just says that a multiply instruction will exhibit a fast path, like the path on the right-hand side, if at least one of its operands is 0, and it will exhibit a slow path otherwise. So multiply is kind of a hard operation to compute in hardware, so we have this fast path for easy multiplication by 0. And roughly speaking, each of these paths, I won't go into all of the details, but you can think of them as a partial, like a Lamport-style partial order on hardware events associated with an instruction's execution. So as an attacker, I can learn a function of the multiply's secret operands if I know which execution path it took at runtime, and I can maybe determine this by timing the execution latencies of multiplies. So clearly, an instruction that creates and exhibits operand-dependent execution path variability is one of these transmitters that I have to worry about. This is now a slightly more subtle victim program example. So again, we do have this transmitter unsafe operand being passed as secret, and now we have another instruction executing alongside it that has a public operand. And this pattern can be exploited on this open source RISC-V processor as follows. So the victim is going to run a store to a secret address. So that's my transmitter instruction. and followed by a load to a public address. And the load, the way it's implemented on this particular processor, it's going to exhibit one of two distinct execution paths that differ right after the load is issued to go execute. And so the load will either stall if it has an address match with a concurrently executing older store that hasn't drained to memory yet, or it will progress to access memory, wrong direction, or it will progress to access memory right away with no stall if it does not have an address match with such a store. So in this case, the attacker, right, can learn the store's secret operand if it knows which path another instruction the load exhibited. So clearly, an instruction that can create operand-dependent execution path variability for other instructions is also a transmitter. So kind of based on this observation that transmitters leak their operands by creating path variability for one or more instructions, we built this leakage contract verification procedure called synth-LC, and I'll pop that up on the slide in a second. But first of all, it takes as input a system Verilog implementation of a processor, so just like a code description of a processor, instruction encodings, and some design metadata. It's mostly just we're going to use model checkers, formal model checkers, in order to do this verification process, and so the model checker needs to know how to interface with the design. And so first, this verification procedure we built, it leverages linear temporal logic property generation from a finite set of property templates that we've decided ahead of time are actually sufficient for this leakage contract verification procedure, in combination with formal model checking to uncover all hardware execution paths that each instruction could ever exhibit on the design. So for example, for the multiply, we'd uncover in this first step, this RTL to multi-execution path, we'd uncover both the fast and the slow execution paths for a multiply. And we proved that by finding all instances of path variability, we've actually found a superset of all of the hardware side channels in the design that could ever leak transmitters' unsafe operands. So we've basically found a superset to all of the possible violations of this non-interference property from earlier on the hardware implementation. Next, we want to identify true positive side channels in this superset that we've gathered. And so this synth-LC component, which comes next, is conducting a symbolic information flow analysis. Again, it's using formal property generation from templates and model checking, and this time it's trying to attribute each instance of path variability that we found earlier to one or more transmitters' unsafe operands under some hardware scheduling conditions. And so, one thing this output gives us, the one thing the output of synth-LC gives us, is we basically reverse engineered from the hardware implementation, a formally verified constant time leakage contract, all these transmitter unsafe operand pairs that are, required by many modern instruction sets today. But synth-LC is actually giving us a lot more. So its intermediate output is a complete set of what we call formally verified leakage signatures for a hardware implementation. And a leakage signature is basically just the highlighted components of what I'll call a leakage function. And this is my other hardware software contract I'm saying enables leakage contract verification. So the first part of this signature is the first part of the function name, which identifies the instruction that exhibits path variability. The second part is the step of that instruction's execution at which it subsequently exhibits a path divergence, at which the source of the variability, if you will. The return value denotes the destination execution steps of the path variability. The arguments identify the transmitter instructions that are responsible for the variability. So this N here denotes an intrinsic transmitter, meaning the transmitter and the instruction exhibiting the path variability are the same dynamic instruction instance. And then the body of the function contains the transmitter's unsafe operands that are to blame for the path diversion. So in this case, it's either operand of the multiply. And then we also get, I sort of mentioned the N superscript, but we get these superscripts for function arguments that denote different hardware runtime conditions that have to hold for some transmitter instruction to create path variability for another instruction. For example, it might be the case that the transmitter has to be older and concurrently executing at the same time as the variable path instruction in order for you to see path variability. This is the case for the store executing at the same time as the load previously. And so why am I telling you all this? So, this function is nice because all of the different components, and you don't need to understand all the details on this slide, but all the different components have these leakage signatures. They map nicely onto all of the requirements for like all of the hardware features that are required to implement a variety of leakage contracts used by a bunch of different defenses. And the simple one we saw was the constant time leakage contract, but there are many more sort of nuanced variants of these, including the one that's used by Cerberus and Protean. So I'll wrap up here. I wanted to, highlight a couple opportunities that I see for continuing to improve hardware side channel defenses based on the work that we've done. So first of all, both Cerberus and Protean, they're trying to leverage information about a code class in order to determine what data should be protected from transiently leaking at runtime. But we don't leverage any explicit, say, type information present within a program, and we're generally operating with C programs where we can make very few assumptions we're just doing register level data flow analyses. We can't make any more strong assumptions like we could if we had a more strongly typed language or if we had explicitly typed variables present within our program. One thing to note actually too is with Cerberus, like technically a taint primitive, it's an instruction that can introduce a secrecy type violation. And for a non-constant address load, technically a non-constant address load can only introduce a secrecy type violation if its output is public. But we actually treat all non-constant address loads as if they could have public output registers rather than filtering them, since we can't do that much filtering. We didn't find benefit from doing whatever filtering we could with just the knowledge we have within a C program. Another thing is these leakage functions or leakage signatures. They provide sort of this precise mapping from transmitter inputs to observable executions of instructions at runtime. And so we think there can be a nice way to use these leakage functions in order to, we could acquire a set of leakage functions directly from hardware and prove that they capture all of the hardware side channels and then use them to map, say, input distributions to a program to full program level observation distributions in order to do things like quantify information flow. As far as sort of like hardware and software, working together, Cerberus was mostly taking advantage of our ability to judiciously constrain control flow. We took a less judicious approach to constraining speculative data flow, but there's, I think, some interesting opportunities to leverage, transient memory isolation, which may or may not be available on existing hardware that's yet to be determined, or fine-grained mechanisms. Both of these ideas have been considered in prior work and could enable something like a Cerberus software defense to operate even more performantly than it does on more general purpose code. Also, for Protean, we right now, hardware will basically assume until it's accessed data the first time that data might be secret. It has to access some data architecturally first to know that the label it read for that data is the correct label. However, we might be able to, say, communicate labels at address translation time if we're able to encode them on pages rather than on instructions themselves, and we could avoid sort of, this declassify on access behavior that we have now and instead do declassify and address translation for lower performance overhead. And this could be paired with things like custom memory allocators in order to be assured that, say, all the data on a particular page is of a particular maybe struct type that follows a specific protect-unprotect pattern for the bytes on that page. And then lastly, this classification of transmitters that we get from the leakage functions, we can use this to, construct more fine-grained hardware protection mechanisms for side channel defenses. So right now, something like, Intel or ARM's leakage contract mode, right, will disable all these optimizations for a whole process or worse. And we could think about, say, disabling optimizations at an instruction granularity and tailoring the way we disable optimizations to be a little bit different based on transmitter types. And then one other thing here quickly on the verification opportunities. So I didn't talk about this in a ton of detail, but the interesting thing about SynthLC and some other work that we've been doing on similar topics, related topics, is we found that, there's a bunch of design specifications or design requirements you might want your hardware to uphold. And one of the key bottlenecks to verifying that hardware upholds these is we rely on experts to manually write formal properties to go check against their hardware design and spend a lot of time manually decomposing those properties to get automated reasoning tools to be able to check them. And we found that for many different requirements you want your hardware to uphold, a finite set of property templates that we instantiate in a bunch of different ways is sufficient to both encode the property you want to check and decompose it to something that is scalably checkable. And SynthLC exploited this insight. We've also applied this on an industry design and saw good results as well. And I think it's applicable for the other hardware side channel attack components that we looked at today. So to kind of conclude with more of an introductory slide that I decided to stick at the end, which is, where does this work fit into the broad world? Computer systems have gotten highly complex, as we all know, and sort of in my computer architecture world, I think of this as giving rise to a couple key challenges. One is this contracts challenge, which I've mostly talked about today, which is that traditional instruction sets lack the detail needed to capture all of the ways in which hardware might undermine correctness, security, and reliability, with the focus of this talk being on security. And so, we're increasingly seeing instruction set architectures today, hardware vendors incorporating new hardware software contracts into their instruction sets in order to, try and repair or fix this problem. And then the second challenge is the verification challenge. This is sort of a staggering statistic from this. Every couple of years, Siemens EDA does this study to see how well hardware verification is going in the industry, and they found that it was actually a 20-year low of first-time silicon success, where they had over 85% of the hardware design projects they looked at had bugs that escaped into first silicon, despite them spending over half the effort on the design process. And we think this problem will continue to get worse as we solve the problem on the left, and dare I say, have the proliferation of AI tools in helping us design hardware. So yeah, this talk I focus mostly on this contract challenge. These are some key takeaways. So I think high assurance really requires us rethinking the hardware-software interface. I gave you a couple examples of this with Cerberus, Protean as hardware defenses and SynthLC as a verification framework. I do think it's worth us reconsidering what hardware and software can independently contribute to solving this problem, because I think we can kind of have our cake and eat it too, like get high performance and assurance if we have hardware software working together more meaningfully. I think in particular, finding ways to communicate rich software analyses to hardware to leverage at runtime as it executes programs gives us the opportunity to both simplify hardware and improve its assurance guarantees. And I feel these ideas are, I talked about security, but I think they're much more broadly applicable to other assurance requirements we might want our systems to uphold. All this work is open source and designed to be extensible, so definitely take a look if you're interested, and I'm happy to take any questions you have.
Hey, thanks for the talk. It was really interesting. So I've noticed that over the recent sort of decades, especially ARM have been getting really interested in providing more formal specifications for their ISAs with sort of the ASL stuff. Are you trying to integrate with that kind of ISA specification as well as sort of doing the leakage contract thing? Is there some connection there between those two things?
Yeah, good question. So the short answer is yes. So at least in our research, when we think about designing new hardware-software contracts, we want them to be designed formally, so there's no ambiguity as to what the hardware-software interface is that we're assuming. And so, yeah, we're generally encoding everything in some sort of a formal DSL or formal language in order to make them sort of executable and unambiguous. Yeah, good question. Thanks.
Thank you for a really fascinating and an educational talk. I'm wondering about your approach to, I guess it's the SynthLC work. You're using model checking to verify the Verilog implementation. What is the I guess I'm trying to understand the soundness argument. I understand that you're able to catch a lot of problems.
Yeah.
But is it comprehensive really? And have you tried to formally stitch that together to show that there's really a comprehensive?
Yeah, good question. Yeah, so the short answer, again, is yes, although right now this formal argument and proof lives in an online appendix because the architecture community doesn't care so much about that, but yes, so essentially what we did in the SynthLC work, not that they don't care, I think they like to know the formal proof exists, but they don't like to look at it. So let me go back to this really quickly here to show you. So basically what we do, here, this is what I was looking for. So basically what we do is, so this is a non-interference property encoding that, right, for basically encoding side channel safety. So your hardware is side channel safe if like the observable execution behavior is indistinguishable for any program given the same public inputs but different secret inputs. And so what we prove is if you have a receiver, an attacker, that can exactly observe the entire execution path of executing instructions, which is actually kind of a strong receiver assumption. So it's these execution paths we actually define as a partial order on the state updates, a cycle-accurate partial order on the state updates that an instruction performs during its execution. And we prove that if you have a receiver that can exactly observe for each instruction which execution path it took, that this procedure will uncover all and I'll tell you about sort of boundedness of model checking and all of that. But the procedure itself, if model checkers were perfect and didn't ever come back with bounded proofs, we would find every hardware side channel in the input design, and every hardware side channel we find would be a true positive. Now, we do get some bounded, so like one of the benefits we think of this template-based approach is we sort of ahead of time come up with a way to decompose this property into like, for the open source design we looked at, although we've reduced some of this property generation a bit to handle industry designs, but we generated about 120,000 simple linear temporal logic properties to analyze end-to-end in open source processor implementation. And each one of those properties tends to take a few seconds to minutes to check and gets unbounded proofs with the commercial tools. But there's maybe like 15% of them, this is again on the open source design, that come back with bounded proofs. And the bounded proofs will impact some of our, soundness or completeness guarantees. Like we may not find every hardware side channel in the design. I would say that's more of a completeness because the model checker couldn't search deep enough to find an execution where it was exposed. So theoretically, we have soundness and completeness, and then we have some, asterisks for modulo capabilities of the automated reasoning tool. But we're trying to do some things to resolve the incomplete results using things like integration with theorem provers and things like that. Does that answer your question? Yeah, cool. I can't see so well from the lights.
Thanks for the very nice talk. So for the second part you described, this Proteon model. If I understood correctly, this basically requires new hardware support to support these new instruction prefixes, so that the hardware can do this better tracking. So I was wondering, well, A, how did you benchmark this, given that, does this hardware actually exist? And also B, is there any interest from big hardware vendors to actually add extensions of this sort to the RSA so that you can actually enjoy this on real hardware? Yeah,
good question. So first, let me start with the instruction prefixes part, actually. We chose instruction prefixes initially because, so x86 actually supports instruction prefixes. So you can add, and part of this is because they have this flexible variable length instruction encoding, you can add these prefixes to instructions, so we add this 1-bit prefix. Although I actually don't think we need prefixes per se, what we could do is say, analyze a program and store the labels for instructions in some special hardware memory that we fetch at the same time of instructions, and so we could handle instruction sets beyond those that support prefixes. So that's one thing. Two is how do we benchmark this? So we use these open source computer architecture simulators, which are these cycle accurate simulators. We use Gem 5 is one common one that has relatively detailed models that have been validated against x86 hardware. They're not perfect, but we think the relative performance benefits we get from comparing like a baseline to our defense are comparable to what we would see on real hardware. As far as industry adoption, so this paper actually will be presented in a month, so this is very new. We did try it on some industry simulators, and there does seem to be some interest, and the performance overheads we saw in the industry simulators are comparable to what we're seeing. So we're implementing actually a couple more slight extensions now, but from discussions with different industry people, there seems to be interest in this. I think particularly if we could get this, what I'm my kind of hot take or claim that we could get 0% performance overhead potentially for this, very simple hardware implementation, I think that would be a lot more buy-in. This is a fancier hardware implementation, and it costs more to implement. This one would be actually quite simple. So I think it is a cautiously optimistic, seems there's interest. Yeah.
Wonderful talk. Thank you very much. My question is if you could provide input to a new generation of systems-level languages to help in your cause, because you mentioned C had its lack of information. What would be, let's say, to keep this question short, the top 3 things you would tell a systems language designer that would help you in this cause? And if the type system is part of that, how rich or powerful of a type system would you desire, such as, say, dependent types? Thank you.
Yeah, good question. So we've been thinking about this, and so, what we've done so far, as I mentioned, is very simple. Like it's register level data flow analyses, and we could actually get reasonable performance doing that. So the level of like sophistication we need from software is sort of unclear to me right now, but I think what is clear to me is that with more sophistication, we will get lower performance overhead, because really right now we're sort of limited by what we can communicate to hardware, how much detail, and when. So if we can also communicate detail to hardware earlier, say at allocation time rather than at access time, that would also be beneficial. As far as sort of what techniques, so I listed a couple different things here, but I think you can view them in a couple categories. So right now, we leverage information about the program's type. So like, what class does it fit in? And also just to clarify, like we're just manually going in and looking and saying, we think this code is in this type, because obviously we just have C code we're dealing with. But so we assume we have the ability to classify code. So that's like the first level, is we'd like to be able to know for sure which code class some function or component belongs to. Second is if we had, say, for example, a language that had memory safety guarantees or strong static types, we could probably do more like declassification through memory dependencies, or more on protection of data just given the code class than even what we are today. And then you could go this extra level of saying, okay, now I'm going to have explicit secrecy typing information, and that would probably do that's probably going to be the most beneficial for this unrestricted code class that I was mentioning. So I think it depends on the code class. For something like maybe a lot of functions in the Linux kernel, which are probably more in this unrestricted class, probably having explicit types and labels is going to be beneficial. For some other code classes, perhaps just the type information along with a relatively strong type system for the language could allow us to do enough type inference. That answers your question. So not 100% sure, but I think there's these different levels that might be applicable for different code classes.
We have time for just 2 quick questions.
It's really cool work. How well does the protection mechanism work when you are combining code that was compiled with and without it?
Yeah, so for code that's not, if we say don't recompile the code, the sort of formal guarantees for the code we get is something that people have called weak speculative non-interference in the literature, which means that any data that the program does not access architecturally will be prevented from leaking, but that's it. So that's, it's something. It's not, it maybe isn't perfect, but that's what you would get for, sorry, I think if I'm not close to this, you can't hear me. That's something we would get for no code recompilation, so that's kind of the minimum. And then it's kind of a pay-as-you-go model after that. So if you're, and I actually think too, kind of related to the instruction prefixes discussion, I don't think we actually need to recompile the code to get the protections we're getting here. I was thinking about this recently. We might be able to just do binary analysis and again store in like a metadata table rather than having instruction prefixes, the labels for each instruction. So we could probably even get around that a bit. But you still need to know the code class if you want to take advantage of the other sorts of. Actually, you could say, if you wanted to assume the code class was constant time, then again, sort of the maybe it's not, but if you assumed the code class was constant time, the formal guarantee, again, that's been coined in the literature is speculative non-interference is what you would get for that program, which means that no more data than is leaked architecturally will leak speculatively. So we can have had those two cases.
Very nice talk, thank you.
Thanks.
I'm not sure this is going to be a quick question.
Okay.
Maybe we can just deal with the prefix of it. So for the last part, microarchitects are endlessly, annoyingly inventive, and it's
Sorry, say that again?
microarchitects, they're annoyingly, endlessly inventive.
Yeah.
And it was not clear to me how much of the microarchitecture you're model checking here. Is this looking just at the pipeline with some separate argument that all of the storage hierarchy is kind of irrelevant, or what's going on?
Good question. Yeah, so I'll answer. You can tell me if I'm getting the question. But we actually are model checking the full design, but there's an asterisk here. So the procedure is, let's call it semi-modular now. I think we can automate the modularity a bit now. Meaning what we can do is we can apply these approaches, say this first step of our procedure, which finds all the execution paths that each instruction can take through the design. We can apply this on like a per module level within the design. So when we applied this procedure to an industry design recently, we applied it to a module of an industry design. And we're model checking that entire module. But essentially what this first step is doing, the reason why we divide this into a find the execution paths and attribute path variability to different instructions operands, we divide into those two steps because we can use single trace properties, just looking at one copy of the design, to find all of the paths. And then we're sort of like saving this like non-interference step for once we've pruned away a lot of the details of the design. Like now we just have these abstract paths we're dealing with. These paths just contain ordering information about instructions updating individual registers within the design, like a partial order on updates to registers, but they don't contain any information about like what values they're updating the registers to. Like if you wanted, we're kind of extracting, if you will, like an ordering specification from the implementation, and then once we get that more abstract model, then we're doing the more complicated non-interference checks effectively over that abstract model. So we're model checking the full design. It's semi-modular in that right now we have to kind of manually go apply it to individual modules. In the original paper, the open source design, which is much simpler, we could look at the full core in isolation and the memory system, like the cache hierarchy in isolation. And we did those two pieces separately, and we stitched together the paths from the individual pieces, and there's some effort to stitch together the paths. And that's why I say it's kind of semi-modular. I think we can clean up with like nice interface invariants and so on, the stitching together of paths to make it less. Yeah.
I want to understand that better, but it will take longer. So
Cool. Yeah, I can talk to you more.
Why don't we take other questions offline? Just one announcement before we thank Carolyn. We're running a little bit behind, so we'll start the next session at 10:45. And with that, let's give Carolyn a round.
your DAO.
That's cool.
Not that I know.
Okay, this mic the mic, so I guess.
Do you have the mic?
Yes, it's there. Near my stuff.
Great. Then I think that's that.
Okay, good. So the volunteers will run around and give them to people. You want the chair? Yes, I'm the chair. Yes. Okay. Yeah, good. Okay. Excellent.
So you know you can adjust the height of the.
Sorry? Yeah, yes, it's good. Yeah, thanks. Good. Welcome to this session on concurrency. Of course, one of the best sessions of POPL'. So we are going to start with a distinguished paper, which will be presented by Alexandre. And for some reason, there are no slides anymore. So what happened here?
No, they will come up, hopefully.
Okay, good. Alexandre, the floor is yours.
So hi everyone. So my name is Alexandre Moine. I'm a postdoc at NYU. And today I'm going to present joint work with Sam Westrick and Joe Tassaroti. And the paper is titled All for One and One for All, Program Logics for Exploiting Internal Determinism in Parallel Programs. So it's still early in the morning. Let's see an example. This is a Dumas function that takes as parameter an integer n, and then allocates a reference r, initialized to 0, and then in parallel adds to r 18.2 or and 42. Let's say the addition is atomic here. And then after this parallel phase, the program asserts that the content of R is equal to n. What can we say about this program? Well, first of all, it's safe if and only if n is equal to 1844. Otherwise, the assertion here will fail and the program will crash. The other thing we can say is that this behavior is difficult to verify in separation logic. Indeed, you have a pointer, R, that is being written to by two concurrent tasks. Let me show you the proof. So it's the same program with more space. And in separation logic, first, when we allocate this pointer here, we get a points to assertion. So we have that R points to 0. Now we face a par. So what is a par, rule of separation logic? Well, it's this one. To verify par ELER, you have to separate, this is a separation logic, to separate your precondition in two pieces, one that will go to the left side and one that will go to the right side. However, here we have an issue because we have a single points to assertion, but we will need it in the two sides, so we are a bit stuck. We cannot split it. So of course, concurrent separation logic is powerful enough to verify this example, but in this case, you need heavy machinery, you need invariance, you need ghost state. There is no need to understand anything here. Just want to display that this proof is difficult. And it's difficult, well, for a good reason. It's painful because this proof verifies that every possible interleaving or ordering is correct. So either so it verifies that the prime is correct, even if the addition of 18.2 happens before 42 or the other way around. But one observation we can make here is that the order of the addition does not matter. Additions commute. So this proof is a bit too difficult for its own good. The remark we can do is that many programs are like Dumas, or what we call internally deterministic. It's a terminology coined by Blalock et al. It means that every action of every parallel task is deterministic with respect to the interleaving. That means that the interleaving cannot be observed by the program. And this is a very cool property to have because it means that you have what we call in the paper schedule-independent safety. So this property says that if one execution of the program is safe and terminates, then every execution is safe. And this property is very cool because it means that proofs become very easy. You just have to verify that one interleaving is correct to deduce that they are all correct. And this is, of course, the Three Musketeers motto, one for all and all for one. And it also means that you can also test a concurrent program efficiently. You just run the program once, and if it terminates, you know that every other interleaving will also be correct. So to draw things here, the general way to verify that a program is correct is to use separation logic. But here what we propose is a new recipe for verifying internally deterministic programs. So we propose to split the safety proof in two sub-goals. The first one is to prove schedule-independent safety, and the second one is to prove that one interleaving is correct and terminates. In order to prove these two goals, we have two program logics. The first one is called Musketeer, and the second one is called Angelic. Then the question, of course, is, wait, are you suggesting that we do two manual proof instead of one? And of course, the answer is no, because we prove that you can verify schedule-independent safety with a type system. So we also propose several case studies, including primitives from this article from Blalock et al. And Musketeer, Angelic, Minidet, this type system, and the case studies are mechanized in rock prover on top of the Iris framework. So here I will first present Musketeer and then present Angelic. So this Musketeer triples. So Musketeer looks like a standard separation logic. You have a triple here, an expression being verified, the precondition P and the postcondition Q, except that the postcondition is parameterized by the return value, V, and a ghost return value. I will say more in a few slides. Such a triple guarantees a hyper property, a for all hyper property that is a bit verbose, so brace yourself. It says that if one execution of E is safe and terminates from a heap satisfying P, then every execution of E is safe starting from a heap satisfying P, and all terminating executions will end on a heap satisfying Q. Well, the important thing to understand is that if we trivialize P and Q, we get a Sandler theorem that says that if we are able to verify the program E, then we know that E satisfies schedule-independent safety. What are the rules of this program logic? Well, Musketeer is almost like a standard separation logic, so you have points to assertions, higher order ghost state, invariance, and almost every separation logic rule. So in particular, we have a rule for creating a points to assertion. So if we do a ref on V, we have a points to on V. Then we have a rule for loading a location. If L points to V and we get L, we have a value V, and L still points to V. And we also have a rule to set the content of location. If L points to V, and we set it to V prime, we have L points to V prime. And we even have a standard par rule. However, there are two key differences with standard separation logic. The first one is the assert primitive, and the second one is how we deal with the existential quantification. So, the reasoning rule for assert. The primitive assert V is safe if and only if V is equal to true. Otherwise, the program will crash. However, Musketeer offers the following reasoning rule for assert. It says that you can verify assert V without precondition. So you can apply this rule even if V is false or even if V is equal to 42. And you deduce in the postcondition that V is equal to true. So obviously this rule does not guarantee safety, but it does guarantee Musketeer's motto. That is, if one execution of say assert V is safe and terminate, then every execution of is safe. Indeed, if one execution of assert V is safe, it means that V is equal to true, and then if V is equal to true, every execution of assert true is safe. And then also be reassured, here we have assert V for a value, but we have a bind rule, so we can reason on assert E for an arbitrary expression E. Now, something a bit more tricky, the existential quantification. This is a small variant of the Dumas program that does not satisfy schedule-independent safety. We have a reference R, and then this program in parallel says R to 1 or to 2, and then assert that the content of R is equal to 1. So of course, this program might fail because it may observe the scheduling, that is, if the left task here execute before the right task, or they will then be equal to 2, and the assert will fail. So Musketeer is sound logic, so where does the proof fail? So we can allocate the points to, we have invariance, as I said, so we can allocate the invariant, even verify the two parallel sets. But then you arrive to a point when you need to eliminate the existential quantification. That is, you are in this state, you know that there exists an n such that R points to n, and then you want to verify E for any possible witness of the existential quantification. And Musketeer does not allow you to do that. So that where the proof fails, we do not have a rule to eliminate the existential. And this is for a good reason here, because the existential here hides the interleaving. It hides which thread won the race. So Musketeer prevents from eliminating arbitrary existential quantifications, but when we know that the existential quantification was chosen deterministically, we have a solution, and it's this ghost return value. So here, to explain the ghost return value, let me first present how we reason about a let binding in separation logic. So this is a standard let rule for separation logic. To verify let x equal E1 in E2 under the precondition P, you first verify E1 under P, and you have to give a postcondition Q prime. And then you have to verify E2 under the precondition that there exists some value that satisfies this postcondition Q prime, and you replace in E, X, the binding with the value V. And most of the time, the existential quantification is used to transmit information from this postcondition to this precondition. So you often have an existential quantification there. And in Musketeer, we allow for that somehow with this ghost return value. So both conditions now takes two arguments, the physical and the ghost return value, and you can think of this ghost return value as an existential quantification in front of Q prime. So this is the rule in Musketeer. You have to provide a postcondition that will hold for some value and some ghost return value, and then you get to assume that there exists a witness of this ghost return value while reasoning on E2. And then you have to, when you reach a value, you have to provide a ghost return value. That can really be anything. All right, so why does Musketeer work? I will not show you the proof, but some intuition. The intuition of Musketeer is that assertion of Musketeers do not describe one, but two executions. You have the left execution and the right one. So assertions are defined, are parameterized by a Boolean indicating either the left-hand side or the right-hand side. For example, the points 2 of Musketeer is defined as a function that takes a side, and if this side is left, you return the left points 2, and if it's right, you return the right points 2. And you can see here the issue with the existential. The existential quantification of Musketeer here is defined as, well, give me a side, and I will guarantee a witness and guarantee then the property. But the witness can depend on the side. So it means that in Musketeer, when we have an existential quantification, actually you have two witnesses underneath. So that's why you cannot open the existential. Then, to a Musketeer triple, intuitively, is defined like this. It's a nested weakest precondition. So you suppose that the precondition holds for the left-hand side. You verify E. Then you have the postcondition for the left-hand side, and then you have a weakest precondition for the right-hand side, so you get the precondition for the right-hand side, and you have to deduce the postcondition for the right-hand side. This WPR for the right-hand side is a standard weakest precondition, and this one on the left-hand side is a weakest precondition that does not guarantee safety, but is otherwise entirely standard. This is, of course, awful to read, and if you read the paper, we have a nice API for this beast that we call chain triples. Back to this Dumas example. So this Dumas example in the introduction satisfies scheduling-dependent safety, so we can actually verify that this program is correct. Well, satisfies scheduling-dependent safety, so we establish this triple that says that for any n, Dumas n satisfies scheduling-dependent safety. The proof is not that easy. You have to use invariants, you have to use these ghost return values, but the observation is that this proof can be obtained with a type system. The overall idea here to guarantee scheduling-dependent safety is that you just need to ensure that there is no read during the concurrent write phase. So we designed a small type system to do that. This type system is called minidet. So it's an affine type system. So you have here a typing judgment, you have the entry typing environment, the output typing environment, the expression, and the type. So it supports primitive notion of exclusive and fractional ownerships, and we extend it with some primitives from this Blalock et al. Paper. We have a soundness theorem for this type system. If you are able to give a type to E, you know that E satisfies scheduling-dependent safety, and the proof is mechanized, and it's done with a logical relation in Musketeer, meaning that for every syntactical type derivation, we associate a triple in Musketeer. And we can type check Dumas, spare you the details, but we can give to Dumas the type into units, so to show that Dumas indeed satisfies scheduling-independent safety. All right, now that we know that Dumas satisfies scheduling-independent safety, we can use this property, and now we know that it suffices to verify that one interleaving is safe and terminates to deduce that every interleaving is safe, and then it means that we can get an interleaving, pick an interleaving to verify. So for that, we introduce a new program logic called Angelic. It looks like that. You have a precondition, you have this run modality that looks like a weakest precondition, an expression, and a postcondition. And the soundness theorem says that if you are able to verify the program E, then you know that one execution of E is safe and terminates. Again, what are the rules of this separation logic? It's again almost like a standard separation logic. You manipulate points to assertion, and it supports ghost state without step indexing in order to guarantee termination. Then these are the rules of Angelic. So you have the standard rule for ref, get, set, and also for assert. So this time for assert, you have to prove that one execution is safe and terminates. So you have to prove that the value is indeed equal to true. Then the fun part of Angelic is that it allows you to pick any interleaving to verify. So for example, to verify run of par EL, you can first verify the left-hand side and then verify the right-hand side. So if I draw a diagram, you can do 1, 2, left-hand side, and then 3, 4 for the right-hand side. But also you can pick the other interleaving. So to do first the right-hand side here, ER, and then the left-hand side, EL. So do 1, 2, 3, 4. But Angelic really allows you for picking any possible interleaving. So for example, you can do 1, 2, and then 3, 4. And we have some general rules for doing that. So to select an interleaving in Angelic, we introduce 2 new assertions. The first one is yielded by E to set that the task pi is currently executing E. And then we have an opaque goal that I describe with this Gothic goal here. So the rule for fork, so to verify run of par EL, you get to assume 2 task identifiers, pi L and pi R. You get to suppose that pi L executes EL and pi R executes ER. And then you get something like a continuation that says that when pi L will reach a value VL, pi R a value VR, and the post-condition Q holds, then you can prove this opaque goal. And then your goal is this opaque thing go. Then of course you're a bit stuck here. And so we provide a resume rule that allows you to resume the verification of any task. So if you know that task pi is executing E, you can resume the proof and reduce the goal to proving a run of E. And then in the post condition, you get to know that pi reached the value V. All right, so the 2 interleavings, these 2 rules allow you to really execute fully one task or the other, but we also have a rule to yield and stop the verification at any point in the proof. So if our goal is run E, we can at any time suppose a new task identifier pi, and suppose that pi executing E, that when pi will reach a value V and the post condition hold, we have the goal, and we just need now to prove the goal, and we can switch to another task. All right, with all of that, we can finally do our proof of Dumas. So of course here you have to call Dumas with the correct argument, 1844. So we first allocate the points to assertion, then we face a par followed by an assertion. So we use the bind rule to focus on the par. Then we face a par of add R18.2 and add R42. And then we can choose the one to verify first. Let's take the left-hand side. So we verify first the addition of 18.2. It updates the points to assertion, as you can guess. Then we verify the addition of 42. It again updates the points to assertion. And then, trust me, the rest of the proof goes through. Here, the observation is that we really made only elementary steps. And in particular, we did not need at any time to split the context. So it can likely be automated. We also have a termination proof here, but because the program is not recursive, well, it's manageable. Okay, at the conclusion, I just presented all for one and one for all, program logics for exploiting internal determinism in parallel programs. The key ingredients were schedule-independent safety, so this property that says that if one execution is safe and terminates, every execution is safe. We have Musketeer, which is a semantic model that captures schedule-independent safety, and we have Angelic, a program logic for verifying that one interleaving is safe and terminates. We have several case studies, so this affine type system with Primitive from Bledot et al., and everything is mechanized. As future work, you can perhaps guess it, we're interested into schedule-independent termination. That is the property, if one execution is safe and terminates, every execution is safe and terminates. But termination is a liveness property, and these kind of things are difficult to verify in separation logic. Thank you, I'm ready for questions.
Thanks to Alexandra for the talk. Any questions? Thibaut?
Thank you for the great talk. So I was wondering, on your two motivating examples, one you add and it works, it's schedule independent, the other one you set and it doesn't, and it seems really related to commutativity.
Yes.
So I'm wondering if commutativity appears explicitly in the logic and in the type system, or if somehow it's a consequence.
Somehow it's a consequence. Really, the logic integrates the notion of commutativity. And does not show in the proof, interestingly. In the type system a little bit, because you have to show that addition commute, for example. So in order to prove that the addition satisfies independent safety, you have to show that it may commute with any other addition.
There in the back.
Thank you for the talk. So the type system that you presented, does it also come with a traditional safety result? Because the schedule-independent safety, to me, doesn't seem to imply that, of course, the program actually executes correctly, right?
Yeah, right. So I think it will. It can come with a safety proof, but we do not provide this safety proof for the type system.
Right, but so I'm imagining if I have my own type system where I want to do, for example, a traditional safety property and also your schedule independence property, do I then have a logical relation and a semantic proof that has two kinds of triples? Could you combine these things in some way?
If you already guarantee safety, you have really no need for schedule independent safety. Because the whole point of schedule independent safety is to easily prove safety.
Sure, but what if I have a type system that says safety up to assertions, for example?
So if you want to do that, yes, you will have two triples, I think.
Okay, thank you.
More questions? Here in the second row, please.
Hi, thanks for the talk. Very interesting. I wonder if you need some fairness assumption to guarantee the result.
We have no fairness assumption for now.
Here, the first row.
Yeah, and so regarding again the first logic and type system, do you support non-determinism in branching? That is, in one you have a conditional, and in one execution you take the first branch, and in the other execution you take the other branch.
We do support it, not at the musketeer level, but at this chain triple level. You can actually verify that as long as you guarantee schedule independent safety. Yes.
But would the type system mean that, to...
So not at the type system level.
Okay. Thank you.
I also have a question myself. So I would expect that in some cases you don't really want to have non-determinism up to equality, but up to some equivalence relation. So for example, whenever you're dealing with, let's say, like data structures like sets or maps, then they're represented on some kind of a tree, and then depending on the order, you might get a physically different representation, but something that is logically the same. Does your work support that?
Yes. I think yes.
Can you say a bit about how?
Okay, yeah. If you want to give a musketeer interface, you will have to prove this. You can just prove the chain triple, so this nested weakest precondition. So you have to express the relationship between the two representation predicates at this level. It does not support the reasoning at the musketeer level, but underneath you can do a semantic proof.
Okay, so you really have to unfold the definition of this
bit, yeah.
WP thing and then reason explicitly.
I think for now, yeah.
Do you think there is any hope of providing like high-level rules?
Yes, I hope, but I don't know yet.
Okay. Any more questions? Okay, then I have one more. So suppose you have like you have a musketeer and an angelic proof. Then from this together you get like some kind of like safety at the meta level.
Yes.
But do these two things together imply like an ordinary iris WP?
Yes. In the proof, like when you extract the standard, when you extract the meta theorem in the end, you actually go through a standard iris weakest precondition.
So maybe let me rephrase. So suppose you have a program where some part is makes use of is internally non-deterministic, and the other does do all kinds of weird stuff that wouldn't fit.
Oh yeah, no.
Can you then verify that part, the difficult part, using like the standard iris invariance, and the other part using your?
No, we don't support that yet.
Any hope?
Yes, again, very hopeful, but yeah, I'm not sure.
So you don't have a concrete idea yet?
No.
Okay, sounds like a nice future work. I think the next speaker can set up, and if in the meantime there is a very short question, feel free to. Okay, I think we can thank Alexandra and. The next speaker will be Guillaume. So let's welcome Guillaume.
Thanks. Yeah, thanks. Hello. So this is a work by a lot of people that are shown on screen about library for remote direct memory access. I assume, of course, that you have no idea what remote direct memory access is. So we're going to start with a simple diagram of what a computer is. You have your CPU, you have a main memory, and then you have a lot of stuff that is plugged in, like input, output, storage, graphic cards, whatever you want. One of those components is the network card. NIC stands for Network Interface Card, that is connected to the rest of the world. And all these components in your computer has what we call DMA, which is direct memory access. They can read and write from your memory. And engineers got a very smart and very frightening idea, which is that technically you can connect multiple computers and ask the network card to just copy data from memory to memory, which is not at all the way to communicate usually. Usually if two computers want to exchange data, one CPU has to pack the data through layers of abstraction, send it over, and the other CPU has to unpack everything, parse everything, and handle the data. Here is just really copy and paste. And if you want to push the limits of computation in high-performance computing, data center, etc., you can have higher throughput and lower latency if you do this. But the behavior is a bit weird. We have a semantics of this from a paper 2 years ago, and I'm going to show you a very simple example to start with. So we have two computers, a left computer that has a location X, and on the right, a second computer that has a location Z, two computers separated by two vertical bars. The second computers do absolutely nothing. There's no second CPU. And we have one computer on the left that does two operations. One is an RDMA operations. So Z is a remote location, so we put a tilde to show that it's over the network. And we ask to read the copy of X and copy it into a remote memory Z. And then the CPU has a second operation, which is to modify the value of X. So if you do things in order, what you would expect, of course, is to have Z equals 0. That is just executed line by line. And because RDMA is very weird, we can also have Z equals 1. And the way it works is that first, the first operation is offloaded to the network card. And then the whole point of the technology is that the CPU and the network card work in parallel. So the CPU is allowed to continue execution while the RDMA network card copies data. And what can happen is that the CPU goes faster, modify X, and then the network card reads the value of X to send over. And this is very weird because in any programming language or software or whatever, you don't want those kind of reorderings. You can stop it if you really want to, and the way it works is that we have an operation called POPL'. Basically, when the hardware, the network card, finishes an operation, like Z assign X, it creates a completion notification, some kind of piece of information to say that's finished. And when you poll, the CPU reads into this hardware memory to pop one completion notification, and so you know the operation is finished. And if you do this, you stop the reordering. Problem is, because you communicate with the hardware, it's not very, very stable, because if you have another completion notification in your hardware from a previous operation, the poll is just going to consume it and tell you that the previous operation that you don't care about is finished. And now you can still have this reordering, which means that even if you have a piece of code that works, you can't copy-paste it and hope that it does the same behavior, because there's communication with the hardware. All right. In RDMA code, we have two main issues. The first is that everything is very low level. Because you need to communicate with the hardware, if you want to create a program, you just have a guide that tells you, here's how you communicate with the hardware, and good luck. There's no libraries, there's no high-level definitions, and you can't copy-paste or reuse your code. The second problem that goes with the first is that they don't have a culture of trying to verify or explain what their program is and check that it actually works. We try to fix all of this. First, we have a very simple abstraction of RDMA TSO that I showed before that abstracts away the communication with the hardware, which means that it becomes modular and you can copy-paste your code. And on top of this, the important part is we created several abstractions of libraries on top of RDMA so that you can forget that you are using RDMA and have fast performances. Then we have a new mathematical framework that we call Mowgli, which is used to verify programs with weak memory settings like RDMA, with a local soundness theorem that I will talk about later. And the point is that we can use this new mathematical framework, Mowgli, to certify and check that our implementations actually works. So very quickly on Loco for Library of Composable Objects, it's an RDMA library written in C++. And the main point is that we have a small wrapper around the hardware operations of RDMA that uses one thread manager. So we have one manager that is in charge of talking to the hardware, and then you can write your RDMA programs talking to this manager. So everything is abstracted away, and you don't care about polls that don't take the right operation. So everything becomes modular, which is an important point. On top of this, we have multiple levels of abstractions and libraries. So we have things like low-level libraries, broadcast, for sending quick messages. We have things like distributed objects, ring buffers, queues, that work like shared memory. We have things like locks for synchronizing threads. So we have a kind of a range of applications. And on top of this, we even have a high-level library, which is a key-value store. So basically a database that is built on top of all of this. Thanks to the work of our US team, and mostly George Hodgkins, we have very high performances. We have two examples here, benchmark, so higher is better, as usual. On the left, you have benchmark for broadcast, which is a low-level library for quick communications of results. And our comparison point is MPI, for message passing interface, which is a standard in high-performance computing for distributed computation. As you can see in MPI, as long as you stress the system a bit, performances are very quickly degraded, and in RDMA, everything is fine. On the other side, you have a high-level library, so a key-value store, which is a database. And the main comparison point we have is Redis. You probably heard of Redis. It is the most widespread database software out there, and it does not use RDMA, and as you can see, it is lagging behind. The other two, Sherman and Scite, are RDMA softwares for databases, and we still beat them. What I mean by that is that even though we have a modular approach for RDMA, even though we are also formalizing our tower of abstractions, we still have better performances than specialized software. So that's great, but the main point is that we need to check that our Loco actually works. And so we need to formalize all those libraries and all those intermediate steps. So I'm going to start with a couple examples of libraries and how we can try to formalize them. One library we have in Loco is a ring buffer. So you can see it as a single writer, multiple reader queue. So one thread is sending data once in a while into it, and other thread is able to receive from this queue. So you have to have the syntax somewhere. So send will take a location and value, and receive will take a location and try to return the value, or bottom if the queue is empty. And at some point, you also need to define your semantics, how you expect your ring buffer to behave. So for instance, if one computer sends a value and the other computer tries to receive, you need to express what kind of outputs are allowed. And in this case, what you would expect is either the send happens first and the receive will return 7, or the receive runs first and rinse bottom because the queue is empty, and the send will add it later. So if you want to specify this library, explain what is allowed or not, what it would look like is that you would have this syntax, some explanations about what kind of behaviors are allowed, and those dependencies that we might need later to say that one operation happens before the other. Another example of library would be a barrier. A barrier is used for synchronization across a network. So the syntax is very trivial, and the point is that threads don't execute at the same speed, and once in a while in a computation, you want to resynchronize everything. So barrier is a way to reset, to create a checkpoint that all threads need to reach. So you can morally split your program into whatever is before the barrier, then the barrier synchronizes, then anything that is after the barrier, and you can repeat it any number of times to split your program. And once again, if you want to give the specification of this library, you would expect something like giving the syntax, giving the constraints, as in you have as many numbers of barriers in each thread, and your synchronization between your barriers. Now, the important part is that now that we have two libraries, you can notice that programs are allowed to use any number of libraries. So here is an example where we have one ring buffer, one barrier, two computers. The computer on the left is sending some data, and then the two threads on two computers are synchronizing. And then later, the second thread is trying to read from the buffer. If our libraries work as intended, you would expect that receiving something here should return 7. You don't want to return none because it would mean that the barrier is not doing its job. And so the point of a modelization, formalization, is that you should be able to show that none is not possible. Otherwise, your model is useless. And so we need to model a notion of execution, what a program is allowed to do. And we want to show that by contradiction, let's say there's an execution that returns none, we need to find a problem somewhere in this execution. There's two kinds of problems. Either one of the libraries is not respected. So for instance, you can't receive 42 just because the ring buffer library says you can't return 42. Or you need to find a dependency in between multiple libraries. So we do it with declarative semantics, which means that every function is represented by a vertex in the graph. And so for instance, here you have the first thread that sends some data and then synchronizes with a barrier, and the second thread that runs the barrier first and tries to receive. If we assume that the second thread receives none, we are in this situation. And now we can use the semantics of our two libraries, which is that barriers synchronize together, and that if you receive none, it means that you receive before sending. And once you're in this situation, you have a dependency cycle in between your different vertices in your graph, and thus the behavior is not allowed. And so you can claim that A is not none at the end. Great. We do have a small issue, though, is that I never justified those arrows. They sound reasonable because the program order executes things in order usually, in almost all programming languages, but not in RDMA. And so how do we justify that things stay in order in between two different libraries? If you probably remember the example from 2 minutes ago, if you ask the network card to read something and then you modify it, they can be reordered. So it's not at all obvious when things can get reordered or not. So how do we know this? There's one case where we do know it, which is a paper from 2 years ago about the semantics of the base RDMA hardware. In it, we can show that the hardware has a finite number of operation categories that we call stamps. And basically, you have a table that tells you for each pairs of hardware behavior, can they be reordered or not. So for instance, the example before, if you ask the network card to read something, and then you have the CPU that writes something, you have something that tells you that no, the ordering is not preserved, they can be reordered. And so the example above, you can have Z equals 1. But that's only for hardware, and we're talking about higher level libraries that are built on top of this. And so how can we define for libraries if they can be reordered or not? We're not going to have a table with thousands of lines and columns for every library that we can imagine, of course. So what we do is we simply keep the same table. We just say that the hardware behaviors are going to be categories that we care about, and we are going to ask when we specify a library to explain what kind of category of behaviors they resemble, they behave as. So when you define a library, you have to give this category of behavior. You might have multiple as well if one function behaves as multiple effects. So the real specification of the ring buffer in our Mowgli framework is going to be what I've shown you before, syntax, semantics, but also saying that a send behaves as a network card write, and that receive behaves as a CPU read. Similarly, for the barrier, the real specification is what I've shown before, plus saying that the barrier behaves as a fan send read. And so now, if we go back to our example of a program, we send on the left, we synchronize, we receive, and we want to show that none is not possible. This time we have more information. So the real declarative semantics graph that we have is this one, where we know that send behaves as a write, barrier as a fence, etc. And now we can use the rest of our semantics, saying that barriers, oh sorry, my bad. Yes, and now that we know that a send behaves as a write, implicitly using this table, we know that a CPU writes, a network card write before a fence synchronize, and we know that two reads synchronize as in they execute in order. So now we have a real justification for these dependencies. And now that we have this, we can use the semantics of our library, saying that barriers synchronize together, as before, and that if a read reads none, it means that it executes before the send. And now we do have a cycle of dependencies that is properly justified with all 4 steps. And so this execution is not allowed, and you can't have A equals none at the end of the execution. So at this point, we are able to specify libraries, explain what is supposed to happen. We are able to explain programs and executions and what is supposed to happen, and we can tell if a program can have some output or not. The last one that we need is implementations, because we have a tower of implementations in our local library, and what I've shown you so far is how to specify each of those libraries one by one to explain what is supposed to happen. And now we need to check that our code or implementation actually behave as expected. So programs can use any number of libraries in here, or libraries that don't even exist yet, and we can implement libraries using other libraries. And what we want to show is that our libraries work implicitly, that if you just inline the code of your implementation, everything should be fine. And we need to formalize this idea. So if you have an implementation I for some library that is implemented using other libraries, what we really want is a notion of soundness. So soundness just means that everything is going to be fine. In any context, if you can inline your operation, you have the same behavior. So we have for all lambda, which is an arbitrary, that's a very hard word, sorry. Arbitrary lambda, the arbitrary set of libraries. You have a program that is using any library in lambda plus L. And what it says is that if you inline your implementation for your library I, the outcome after inlining the code is going to be included in the outcome that are allowed by those libraries, including L. Which is exactly what you want to show, because it means that in any case, inlining is fine. The problem is it is very hard to find, because you start with some lambda that you don't know anything about. You start with a program that uses any number of libraries you don't know anything about. And if you just want to prove this, you have nothing to start with. So what we did is we also have a notion of local soundness that is library specific. I'm not going to give the formal definition because it's a bit ugly. You have a paper for that if you want. But basically, when you specify a library, you're going to give a few guarantees saying that you synchronize with previous operations or you synchronize together, the arrows that I've showed you. And local soundness is just to check that in your implementation, those dependencies are carried over and are respected. Everything that you promised in your specification, you can find it in your implementation. And the important part is that it is very easy to show because you only have to focus on your implementation, on what you wrote and your library. And we have a meta theorem that says that local soundness implies soundness. So if your implementation locally preserves what it has promised to do, then in any context, everything is going to be fine. And this is important because it is a meta theorem proved once. And so if you want to create new libraries, new implementation, and build on top of it, this part is already done, and so you just have to focus on local soundness. Oops, my bad. Local soundness, and if you can manage to prove local soundness, you have a global soundness for free. So as a quick summary, we started with RDMA TSO, which is a hardware semantics of network cards. We generalized it into some modular version with a bit of abstraction, and on top of it, we built multiple RDMA libraries that are competitive compared to state-of-the-art communication technologies. We also have a new mathematical model, Mowgli, that can be used not only for RDMA, but also for other memory models to check the executions of programs. We have a notion of local soundness that implies soundness and makes very easy to check that one implementation behaves as expected for these libraries. And of course, the important part is that we checked a good chunk of our local libraries and formalized it and checked that the implementation is correct and behaves as expected. There have been some progress since on other libraries and extensions to RDMA, but I won't talk to it about it now. So that's enough for now. Thanks.
Thank you, Guillaume, for the talk. Do we have any questions? Yes, here, please.
Thank you so much for the talk. So you showed that you use barrier to synchronize send and receive. So what if you have like a third process, for example? Would it also need to call that barrier, or is there a way to restrict the set of processes with the barrier effect?
Yeah, in our library, when you create a barrier, you can choose a set of threads that are affected by this barrier. And so you can create a barrier for just 2 threads, or you can create a barrier for all threads. And that's why we have different locations B. You can have B1, B2, B3 that are all tied to one specific group of threads.
Thank you so much.
Ralph there?
Hi, thanks for the nice talk. So I was wondering, you showed these very impressive performance results. what are you doing different than the prior RDMA libraries? Like why is it faster? I mean, faster than Redis, that's not too surprising, I guess, if it doesn't use RDMA. But the other RDMA libraries, like what's the difference between what you are doing and what they are doing?
Honestly, I don't have the answer to this question because I'm, I'm not really into the implementation side, but we can talk with George at the break after it. Or if you can pass the microphone to George.
Nutshell, I think it's mainly a improved polling mechanism on the back end. An improved polling mechanism on the back end for completion of operations is the biggest thing, and there's a few other smaller things.
Any more questions?
You mentioned that the set of effects have to be associated. It sounded like it's associated manually to these implementations. Perhaps this is kind of just like a trusted aspect, or, and actually, follow-up question on that, like, this also presumes that it's compiled into exactly the hardware operations that you claim it is. And so that would preclude any compiler optimizations or something that might rewrite into a different set of hardware operations. I don't know, can you say a little bit about that?
Yeah, first, yes, it is attributed by hand, as in when you write your library, you're explaining what kind of behaviors it has, the reordering of other libraries is fixed, so you have to define it by hand. Implementation is fine because you can implement one strong behavior using multiple smaller behaviors that are weaker, so that's absolutely fine. You don't have to use the same in the implementation, as long as it is at least as strong through other kind of dependencies.
I have a question myself. So this work looks impressive, but it also looks extremely difficult. Things that I like to do is to formalize stuff in the proof assistant. So I know you have done some proof assistant work in a former life. So if one were to do this in the proof assistant, do you foresee any challenges?
I think it should be fine, mostly because there is a similar, this version that does not work, there is a ROC implementation of this version. And so I assume that extending it to this version should be doable for someone that knows how to do ROC properly. So I think it should work.
Okay, so parts have already been done in ROC in prior work?
Yes.
Was it by you or by others?
By Victor and other people that helped us for this paper.
Okay, that sounds interesting and cool. Any more questions? We still have a couple of more minutes, so don't hesitate to ask. Okay, then I think we should thank Guillaume, and we can take a minute to take a breath while the next speaker sets up.
Sorry.
Going to restart at 35 strict so that people have the time to come in if they come from another talk.
If you want to, you can adjust height. Not sure why that does this. All right. Can you hear me like this? Yeah, I think you should be able to. Yep. Okay.
Okay, welcome to this next talk in the concurrency session. So our next speaker is Alexander, who will be talking about Daphne MPI. So welcome.
Thank you so much. Thank you for joining the session. So I will talk about Daphne MPI, which is a Daphne library for verifying message passing concurrent programs. And this research is joint work with Antero Mayer, Harry Sunder, and Jeff Foster. So I would like to start to briefly talking about MPI and what it is. So MPI stands for Message Passing Interface, and it is a standard that is widely used in high-performance computing, and it describes an API for C, C++, and Fortran, but there are libraries for other languages that also allow you to write MPI programs. And it is great in situations where you have highly structured communication, such as in partial differential equation solvers. So at the bottom of the slide, you can see an example. This is a solution for the heat diffusion, PDE, and this yellow rectangle is supposed to be a heated area, and it is surrounded by cold purple area, and then as time progresses, the heat dissipates. And so, as you can imagine, this kind of simulation is very local in a sense that in order to determine the value at a given point at time t, you only really need to know a small area around that point at the previous time step. And that means that it's very easy to parallelize because you can assign each process on your computer a stripe of a domain or maybe a cell of a domain, and most of the computation process can perform by itself, and it only really needs to communicate along the boundary with the other processes. So a bit more formally about MPI, and specifically the setting that we target is we target the setting with no shared memory, which is very typical as a standard, right? Also no dynamic process creation. So outside of some edge cases, right? When you run MPI programs, you specify the number of processes that the program will use, and that number does not change throughout the execution. Now, a program can support different number of MPI processes, right? But once it starts executing, that number doesn't change. And a few more things that stand out is that in MPI, messages may run asynchronously with the initiating process. So a process initiate 10 receives and 10 sends, then do some computation on the side, and then decide to wait on them in some particular order, right? And also messages can be of arbitrary size. So it's not just passing an integer, you can pass a matrix of values. And it's, as you can imagine, very easy to make mistakes when writing MPI programs. So our goal is to verify that such programs are deadlock-free, that they terminate, and also to show functional equivalence with a sequential implementation. Because intuitively, it's much easier to make domain-specific errors that are difficult to identify when writing parallel code. So if you can prove that your sequential implementation is the same as the MPI implementation, then you have assurance that your MPI implementation is also correct. Now, a lot of prior work that specifically targets MPI mostly deals with model checking approaches, right? And so they often restrict the input or even the number of processes that are running the program. So our goal is to do not have that restriction. All right, so with this in mind, let me introduce our first contribution, which is Daphne MPI, and it is an MPI library for the Daphne programming language. A few words about Daphne. So Daphne is an auto-active verifier, so that means that it fills in low-level proof details for you. It enforces termination by default. You always have to prove termination, and it is great for proving functional equivalence. There's one problem. Daphne natively does not support concurrency, right? It's not designed for that. It's a sequential program verifier. So we want to use what it gives us, but we can't because we're trying to verify MPI programs. So in order to solve this challenge, we introduced a library. So it's not an extension of a language. It's code written in pure Daphne that you can just import. And it essentially makes MPI communication deterministic from the verifier's point of view. And it allows us to verify MPI programs by requiring the user to specify the communication topology up front, and then requiring the user to satisfy preconditions on MPI API methods that Daphne MPI adds. All right. So let me show a small example. So a very simple MPI program. So here you have n processes. And they do the same thing m times, m iterations. So there's a loop, and something is repeated. And what is happening is that there's some computation that is local. We don't care about that. What we care is that process 0 sends a value to process number 1, and process number 1 sends a value to process number 2, and so on, right? And then in the next iteration, the same thing happens, and then the next iteration, the same thing happens, and so on and so on. So if we want to describe the structure of this communication, like the whole program, the entirety of it, we really want some way to distinguish between the messages being passed. Right, and so the idea here is that we want to assign a unique tag to every message, right? So that first message that process 0 sends to process 1 is going to be tagged as 0, for example, and then the message that process 0 sends in the next iteration is going to be n-1, and so on. And fortunately, you can do this in MPI. MPI allows tagging messages, although MPI does not impose the restriction that they should be unique, so we do. So in Daphne MPI, the tag for a message has to be unique. Why is this helpful? Right, because if you keep this picture in mind, right, you can see that you can probably define the sender and the receiver of each message as a function of the message tag. And so this is exactly what we ask the user to do when they begin writing their MPI program. So they create this MPI world object, which is what you have to do in any MPI library. But in Daphne MPI, there are also some ghost arguments that the user has to fill in, such as identifying the sender and the receiver and the payload as functions of tag and size, right? Size being the number of processes and tag being the specific identifier of the message, right? So for the example that I just showed, you can just take the remainder of a tag by dividing it by the number of messages that are sent in each iteration, and that gives you the sender, for example. And then after you create this object, the process may then query for its own rank and the size from that object. And these are uninterpreted. Everything that follows, so the code that follows, it cannot assume anything about the processor's rank, right? So you can branch on it, right? And if you are in an if condition following some constraint on rank, then you can assume that. But otherwise, it's uninterpreted, and the proof has to work for that. And we also support collective operations. I'm not going to go into too much detail here in the interest of time, but we support barriers, gather, all reduce, and it's generally possible to add collective operations and interleave them with regular point-to-point messages. Now, how is this topology enforced? So anytime the user wants to receive or send a message, they have to call the corresponding method in Daphne MPI. And that method has preconditions, requires clauses in Daphne, that check that the receiver and the sender are just as they are specified, has been specified by the user originally. And also, if you are receiving, for example, then you also get a pause condition that allows you to assume that the value that that is being put into the destination array, destination matrix, that you, is exactly as specified by the user, right? It's the payload of the message. And there are also some other preconditions that ensure an ordering of message tags, because of course we're in a concurrent setting, so we want to prevent deadlocks, and so the idea is that the process must wait on increasingly larger tags, and that prevents deadlocks, and of course you also should not wait on a tag that you've already used before, and the tags have to be correctly intervened between the barriers. All right, so I've introduced Daphne MPI, but I haven't really talked about what we prove about it, right? So I've mentioned deadlock freedom, for example, but right, how are we sure that it's actually deadlock free? And also I haven't really talked about the programs you can write with Daphne MPI, so that's going to be what I will do in the next few minutes. So in order to prove properties about Daphne MPI programs, we introduce a core calculus that abstractly describes all the programs that you can write in Daphne MPI. And so it's an imperative language. It has some common control flow constructs that you can expect, conditionals, loops. It allows setting variables. Environments are local to the process. And importantly, there are 4 commands that are specific to MPI communication. So I receive, I send, wait, and barrier. So barrier synchronizes all processes, as we saw in the previous talk, But then we split receives and sends into two parts, as you can do in MPI. So there is an initial receive or immediate receive, and then there is a wait, and the same for send. The idea being that a process can initiate a message transmission or start receiving a message, but then do something else in the background, and only when it calls wait does it actually block until the communication is completed. And this first argument here for I receive and I send is the tag. It's an expression that evaluates to the tag of a message, right? So we don't even specify the sender or the receiver explicitly because we assume that we have these functions that the user provides that map a tag of a message to the sender, receiver, and the payload. So in the paper, and I encourage you to look at it for a more detailed description of this, we prove that for any program that you can write in our core calculus that also respects the properties guaranteed by Daphne MPI, there exists no reduction from the initial state to a deadlock state. Right, so for any command in the initial state, right, all processes execute the same command, regardless of what it is, you will not get to the deadlock state. Very briefly, the outline of the proof. So the idea is that you prove this by contradiction. You suppose that deadlock is reached, then you pick the process that is blocked on the message with the smallest tag. It, of course, has a communication partner, right, for that message. It's either sending that message to some other process or receiving from some other process. And then you can just look at that other process of the communication partner, and you see that whatever its state, whether it has terminated, is blocked, or is running, you actually get a contradiction. So a deadlock cannot happen. So something that is particular to our core calculus and specifically operational semantics is that we model some of the aspects of MPI quite closely, and so I want to highlight one of these things, which is the non-deterministic behavior of send operations. So in an MPI, you can have a send that completes before the receiver initiates the transfer of the message, right? So the way this works is that, so here is a timeline from left to right, it's time, right? So if a sender initiates a send, that message could then be buffered by MPI runtime. And so when the sender calls wait, it is possible for the sender to actually continue execution, and from its perspective, the message has been transmitted. Even though the actual transmission of the message happens later when the receiver calls receive. But as I mentioned before, in MPI you can transmit very big messages. And so in fact it's quite possible that MPI runtime cannot buffer the entire message. And so in this case actually the sender does block, right? And it will have to wait until the receiver calls by receive on its own end, and only then will the message be transmitted and both processes can unblock. Right? And so our operational semantics allows for both things, and so the proof works for both things. All right. Okay, so a few words about limitations. Right, so we don't support some things in the MPI. I'd say it's a very big standard. So we don't support wildcard receives. So a receive always has to have a specific source, right? The message has to come from a specific source. You cannot receive from an arbitrary source. And we also do not support multiple communicators. So that means that all collective operations have to work for all processes, right? So if you have a barrier, all processes wait on that barrier. And also we model collective operations as barriers in the core calculus. So if you've seen if you remember core calculus that I showed, it only has a barrier as a collective operation. Now from the perspective of a deadlock freedom proof, it doesn't matter whether it's a barrier or some other operation. But of course, for the library itself of Daphne MPI, in order to support gather, for example, we add additional specifications that are not reflected in the core calculus in order to reason about the output of those operations. Right, so now let me move to our third contribution, which is a set of free verified partial differential equation solvers that use MPI. So these are solvers for the linear convection, Poisson, and heat diffusion PDEs. So the linear convection models the transmission of a wave to sort of a constant speed, and so you can see the communication topology for it at the top left. This is what I've showed you earlier. So Poisson has a bit more complicated communication structure because each process has to communicate both with the process on the left and the process on the right, and entire rows of data are being sent. Right, so here it's columns, but it's transposed for visibility. But so entire rows of data are being transmitted, and also in the end there is a conversion criteria. So there's a check after each iteration to determine whether or not the convergence has been reached. The last one, the heat diffusion, is in some sense the most complicated one, because in this case entire matrices of data have to be transmitted between processes, and these matrices can overlap. So, for example, we support a situation where a process sends chunks of data to the process on the right and process on the left, and it actually sends some of the data to both, right? So this overlap here in the middle. All right. Aside from implementing these PD solvers using MPI, we also implement sequential versions of these, and we prove them to be functionally equivalent through bitransitivity with a functional specification, right? So the idea is that you write the sequential implementation, and that is the one that's easiest to proofread. You can show it to a person who knows really well how to write partial differential equations code, and they can read it and check it, essentially. Then there's a functional specification, which is, at least subjectively to me, much more difficult to read, but it's definitely much easier to write proofs about, right? And then there is the MPI implementation, which is the most efficient and the most difficult to reason about. So the idea is that you take a functional specification and you prove it to be equivalent to both sides. A little bit about evaluation. So we've actually compiled all of the code that are written to Python and ran it with different number of processes. Right, so here for each of the 3 benchmarks, you can see a graph that shows the running time as a function of the number of processes, and you can see that it goes down. So the first point here is the sequential version, and then all the subsequent points are the MPI version with different number of processes. So that shows that the programs that are written, they're not just functional equivalent, they don't just deadlock, but they actually do give us a performance boost. And this jump at the end that you see seems to be specific to the machine that we ran this on. One of the artifact reviewers didn't see that, for example. So the main trend is that it goes down at the beginning. So another thing that was particularly interesting to me is to measure the percentage of ghost code, right? Essentially a verification overhead or a proof complexity metric, if you will, right, for these programs. So here you can see for every benchmark and every part of the benchmark, so specification, the sequential part, the parallel part, and maybe some shared code that's used by both implementations, you can see the number of lines of code and also the percentage of ghost code. So the percentage of code that's not compiled, that's only used for a specification. And of course, it's much higher, that percentage is much higher for parallel versions. Even though a huge amount of proofs of a proof is completed automatically by Daphne, right? So these specifications are only really necessary when you deal with some gnarly modular arithmetic, for example, and you need to guide the verifier. All right, so to summarize, we describe an approach for introducing MPI concurrency into sequential program verification context, and we implement this specifically for Daphne as a Daphne MPI library. We prove that Daphne MPI library guarantees deadlock freedom by enforcing an ordering and message tags. And we use Daphne MPI to verify 3 partial differential equation solvers, including proving equivalence between the MPI and sequential implementations. And you can read the paper, and I will be happy to take any questions. Thank you.
Thank you, Alexander, for the talk. Any questions? I see Joe there.
in these examples that you did the functional equivalence verification for, are they using floating points for these calculations? I assume PDE solvers need floats.
Right. So this is yeah. So in Daphne we use reals, and so we don't model any. If that's your question, right? So we don't model any kind of hardware specific issues that can arise from floating point computations, right? So that would be an entirely different line of work. But yes, the idea is that once you compile them, they do. Yeah.
Hi. One thing I'm curious about, the starting point, just the setting for the work, is this very structured message passing setting, right? It's like statically I can predict exactly the messages that are sent. I can give a unique tag to every message. I mean, I wonder if you could just maybe speculate a little bit about it. Maybe you've thought about it a little bit, like pushing this idea a bit further. Can I do data-dependent message passing, where whether or not I send a message depends on a certain data condition? I mean, this could be, for example, a sparse solver. You only send a message if you actually have a non-zero at some position. These sorts of tricks, significant improvements in message volume, you can get significant performance improvements, right? I don't know, have you thought about these kinds of settings, and would the technique scale to these as well?
Right, so thank you for this. So yeah, so this is definitely a direction for future work. I think the closest to what you're saying, which is a bit simpler, but still is what we did for Poisson, which is that so there is a convergence criteria, and you don't know, for example, the number of iterations a priori, right? And so at the end of each iteration, each process decides based on the output of the all reduce operation, which checks the convergence criteria, so it decides whether or not to continue execution. So it is data dependent in that sense. And yes, of course, in the future, I think an interesting line of work would be to explore these more complicated settings. So this is what we want to do, but still work in progress, or in future work. Yeah.
Hi, thanks for the talk. One of the interesting things about MPI is that it has both blocking and non-blocking versions of a lot of different communication primitives, and they're actually allowed to intermix, so that you can have like a blocking receive matching with a non-blocking send, etc. Do you model that at all, and how do you reason about that?
Yes, so we do have, well, to be precise, we model the immediate send and immediate receive and blocking sends and receives, and it is entirely possible for one process to use a non-blocking version, an immediate version of a send, for example, and the other process to block on the receive. So there is no restriction in that sense. The way we model them is, right, so in the core calculus, we differentiate between the beginning of a receive or send and the wait, which is where the block can happen. And so if you want to write a blocking send or receive, you simply follow a receive by a wait or send by a wait. But you're allowed not to do that. You can like have a ton of different computations and other communication operations in between, right? The specific way we model this is by explicitly modeling the buffer. In our operational semantics, we keep track of the sort of internal MPI buffer, and that allows us to say that a receive can, a send can transfer a message to the buffer, for example, in the background while something else is being executed. Yeah. So that was sort of one of the main motivations, is to support non-blocking receives and sends.
Okay, any final question? Okay, then my final question is, like, you have your core calculus and you have all the stuff in Daphne. How do you make sure that these things are related?
Sorry, related to, could you repeat that?
So there's the core calculus, and you have the actual implementation in Daphne.
Right.
How do you make sure that the Daphne implementation corresponds to the semantics of your core calculus?
Right, so we don't, right, that's a simple answer. It's fairly small, right? The trusting base of the library is fairly small, so I think that's one way to have some confidence of that. In the future, I think there's definitely space for mechanizing both the deadlock-free improve and potentially this connection that you're talking about. So that could, of course, be part of future work, yes.
Yeah, that would be interesting to do. Let's thank the speaker once more.
Thank you.
So now we are going to move on to the last talk of this session, where we see a familiar face again. We already gave the first talk. So let's welcome Alexander again, but this time to talk about disentanglement.
All right, so welcome again. My name is still Alexandre Moine. I'm still at NYU. This is collaboration with Stephanie Balzer and Alex Zhu from Carnegie Mellon and Sam Westrick and NYU. And so this paper is typed as a type system for disentanglement. So disentanglement is a property of parallel programs, so let me set up the stage for parallelism. This is a small example. We have some data here, wait, it doesn't matter, and then we allocate a reference on this data. CH, a channel, communication channel, and then in parallel we call F, J, and H, and name the result X, Y, and Z, and then do something with X, Y, and Z. And to summarize this program, we can draw what we call a computation graph that summarizes the parallel computation. Each vertex is either a sequential unit of computation or subgraph, and then two outgoing edges are a fork, and two ingoing edges are a join. So here we have F, J, and H. And disentanglement is a property of data accesses. So let's try to classify these memory accesses. For example, here, if we instantiate this H function by a size function that computes the size of the data inside the channel. There are two options when the right task loads or acquires the content of the channel. Either it contains all data allocated by some preceding task, and this precedence notion is important here. So we say that a task precedes another when the first task can reach the latter in the computation graph. So the data can be allocated by a preceding task or can come from a concurrently executing task. For example, it can be allocated by J or F. And disentanglement restricts what a task is allowed to acquire. So in particular, disentanglement says that a task may only acquire data allocated by some preceding task. So equivalently, we can say that a task may not acquire concurrently allocated data. The first remark we can do about disentanglement is that it's a property that broadly occurs. For example, pure programs are always disentangled, but also deterministic race-free programs are also always disentangled. But really the important part about disentanglement is that it enables task-level memory management. So the idea is that you can equip each task with its very own local heap that looks like a tree, and then because you have the guarantee that the tasks do not exchange location they allocated themselves, you have the guarantee there is no cross-pointer here between these heaps, so you can do parallel garbage collection without synchronization. So you can do parallel garbage collection very efficiently. And disentanglement is a property that is exploited by the Maple compiler that is developed at CMU, NYU, and RIT. It's a compiler for parallel ML, so standard ML with a par primitive. It takes two closures as argument, from unit to alpha and unit to beta, and return the immutable pair of the result of the closure after executing them in parallel. So the issue is that because Maple exploits disentanglement, it has to ensure that the program actually remains disentangled during execution. And Maple does that. It detects and manages entanglement at runtime. However, we are at POPL, so how to guarantee statically that the program remains disentangled? And we provided a first answer at POPL'24, where we proposed dislodge a separation logic for disentanglement. However, as you may know, doing a full separation logic proof is costly. So here we try to simplify things, and we propose a type system. So what is the intuition of this type system? Before showing you any rule, the idea is that because disentanglement forbids these cross pointers, it allows for two types of pointers. You have up pointers, so a task may point to a location located by some task may point to some other location allocated by a preceding task, or down pointers, a tag from a parent to a child. And the very naive observation we make here is that for entanglement to occur, so for example, for this task here to acquire some concurrently allocated data, for example, from this one, you need a communication channel between the two tasks. So you need a down pointer for entanglement to occur. So it means that if you only have up pointers, you're safe, and the program will remain disentangled. And this is exactly what the type system will enforce. We will force that every pointer goes up in this heap hierarchy. So the contribution of this work is type D, so type system for disentanglement. The idea is that each type is going to be tagged with a timestamp, think of a region, and the timestamp identifies a task that allocated the underlying value. And the key idea of this type system, as I said, is the pointer invariant. A location may only point upward in the computation graph. We support several features, so polymorphism for both types and timestamps, subtiming, which is a cute name for subtyping for timestamps, and isorecursive types. And again, everything is mechanized, so in the rock prover on top of the Iris framework. So what does a type D type look like? First, we have unboxed type, TOE, which are totally standard because disentanglement care about things that are allocated on a heap. So if you have unallocated things like int or bool, no problem. Then we have two mutually recursive syntax. A syntax for boxed type, so things that are allocated on the heap, sigma, for a string, a ref, a product, or a sum, for example. And then general types, row, that are either an unboxed type TOE or a boxed type sigma annotated by some timestamp delta. And then, for example, we support type polymorphism. And the idea, as I said, is that newly allocated data will be tagged with the current timestamp. Here, if let's say it's delta 0, so if we have a string, hello, we have a string at delta 0, and if we allocate a string, a ref on a string, we get a ref on a string at delta 0 itself at delta 0. So we really have these identifiers everywhere in the types. Now, you might ask something, there is something missing in this figure. What about functions? So in our case, functions are allocated on the heap. They are boxed because they can be closures. We also, that's at the function type, we allow to universally quantify over timestamp. And crucially, function type is annotated by the timestamp of the task it will run on. So syntax looks like that. It extends the syntax of sigmas. And that's our every timestamp delta. Take a list of parameters row, and then here this superscript delta indicates that the function will run on delta. Let me show you some examples. So again, we have this string h, hello, and this r, a ref on world. If we have a function f that sets the content of r to be h, well, everything is all right, because h is a string at delta 0, r is a ref on a string at delta 0, so there is no constraint. You can execute this function at any task. However, if we have this function j that takes as parameter an integer I and sets r to be the string representation of I, then intoString will generate a new string, allocate a string, and because r contains a string at delta 0, we need this string to be itself at delta 0. So the whole function has to be called as at timestamp delta 0. All right, now the interesting part about par. So as we will see, the type of the primitive par is quite non-trivial. So I start by a very specialized type when we have two closures that will return an integer, an unboxed integer. So here this type universally quantifies over delta, the timestamp at which we are going to call par, and two irrelevant timestamps of two closures. And then par takes as argument two closures that have the same type. They say that for any timestamp delta prime, there should be functions that will be executed at delta prime and return hint. So this type really captures that the two closures will be called at some other unspecified task. So this type is admissible, but is really unsatisfying for 3 reasons. The first reason is what if the two closures return the box type? Also, what about type polymorphism? Can we have a polymorphic par? And also, is there a way to exploit the precedence information? Here, I forget that delta prime is a child of delta. And I'm going to answer all of these questions. So what about a box type? So this is a modification of the previous type, where the two closures return a ref of int allocated at delta prime. Now, what is the return type of par? Here, we would like to say, okay, give me a ref int at delta prime, but we have a scoping issue because delta prime is quantified here, and here we are outside of the quantification, so what should be the timestamp of the two return locations? And the intuition is that for disentanglement, everything allocated by a child will be accessible by the parent after the join point. So really, everything allocated at delta prime should be accessible by delta. And we take this intuition very literally. That is, we change the timestamp of the return location. Here, the type we give to par ref int is that par returns a pair of ref allocated at delta. So we forgot that this ref were allocated by some children. And at a very high level, that a good property to have is that you can hide that you used parallelism inside some function call and pretend that everything was allocated by the calling task. All right, now after about type polymorphism. So can we write a polymorphic par? Again, we can try. This is an admissible type in type this. We can say, okay, give me two types, alpha 1, alpha 2. Give me two closures, going for returning an alpha 1 and alpha 2, and we will return a product of alpha 1 and alpha 2. It works, but it's very disappointing because now the two closures cannot return something they allocated. Again, it's a scoping issue. Alpha 1 is quantified before delta prime here, so alpha 1 cannot mention this delta prime. So we solve this issue with a sledgehammer, and we decide to go higher order. So now our types row can take timestamp arguments and can be applied to timestamp. So this means that types themselves have a type, it's called a kind, and a kind either a star, the base kind, or it's a function that waits for a timestamp and returns some kind. And now with that, we can write actually a polymorphic par. So that takes two types of kind, timestamp to star, and then we can require the two functions to give here a phi 1 of delta prime and then a phi 2 of delta prime. And in the return type, we just replace delta prime with delta. So we really replace every occurrence of the timestamp of the child by the timestamp of the parent. Okay, now if we try to take a step back, why is everything working? We have a typing judgment, which is simplified for now. We have a typing environment, gamma, the expression being verified E, the type rho, and the current timestamp delta. And really, in the proof, we need two key invariants. The first one is that locations in the context were allocated by some preceding task. For example, if in our context we have a x of type ref int delta prime, and the current timestamp is delta, we know that delta prime is somewhere before us, so delta prime precedes delta. And then, as I said, we have this up pointer invariant, that's really the key invariant of the system, that says that if we have, for example, a ref on a ref of int at delta 1 itself at delta 2, we know that delta 1 precedes delta 2. We point upward in the computation graph. And when you combine these two invariants together, you know that every accessible location is safe for disentanglement. So, a small remark we can make is that so far the system is very rigid. Indeed, apart from par, there is no way of changing a timestamp in a type, and that really restricts you. For example, here, if we have again our friend h, hello, a string at delta 0, if we start a new task with a par and allocate a ref r here, that is so with a new timestamp delta prime, so it's a ref on a string at delta prime itself at delta prime, and I try to write H inside R. Here I'm stuck, the type system will fail because I expect a string at delta prime, but I have a string at delta 0, no match, too bad. However, here it's perfectly fine to write H inside R because I preserve the up pointer invariant. So we relax everything as long as, so the restriction of writing is unnecessary because we only need the two previous invariants to hold. So we relax everything and we introduce a logical graph to track these dependencies, and then subtiming, which is a subtyping that will allow to type check this example. So logical graph, this is our way of tracking the dependency graph in the type system. So we mount the type system with context, delta, capital delta, and capital delta either empty or record a constraint that said that delta 1 precedes delta 2. And then the way to interact with this context is via a form of bounded quantification. That is, for each function, they can require some constraints to hold, so parameterized with this delta here, and at application time, we will have to check that this constraint hold. And then we can add this information in par. So first of all, this is the final type of par. This is the most complex one. And it says here, like in the two closures that par takes, it says, okay, for any timestamp delta that I know delta prime, that I know will succeed delta, I will run on delta prime. So really, these two closures here now specify that they will be called at some subsequent timestamp. So now we have a time machine, and we can do what we call subtiming. So, for example, if I have a string at delta 1, and I know that delta 1 precedes delta 2 and delta 2 precedes delta, I can restamp my, my string and then get a string at delta 2. So, as you may know, subtiming plays dangerously with mutable state, and we have mutable references in the system. So in the paper, we have a general subtiming rule that allows for shallow subtiming, so subtiming only at the root of the type for mutable data types, but allow for deep subtiming for immutable data structures. Now, to show you a more complex example, this is par4. So par4 takes two bounds and a closure, and we call the closure to every integer between A and B, and does that in parallel. So it really simulates a parallel for loop. It will construct a computation graph that looks like that. And intuitively, for par4, we would like to give the following type. Give me two bound, timestamp delta, at which par4 will be called, and then a closure that will be called on some subsequent timestamp delta prime. And in order to verify this type, it's actually non-trivial. You need something called polymorphic recursion, because you can see here that the recursive call to par4 is made under a par, so we're going to call par4 with another timestamp. And you also need a way of changing a little bit the timestamp constraints here. So we really need some things, but we provide a way of, like, for polymorphic recursion and also subtiming this bounded codification. So we can give the following non-trivial type for par4. Now, the soundness. So this is a sound type system. If we are able to type E at type rho, it's an initial timestamp delta 0, then E is always safe and is always disentangled. The proof is conducted via logical relation in dislodge 2, an improved version of this separation logic dislodge. So to every syntactical type derivation, we give triple in dislodge 2. So this approach allows in particular for semantic typing. So if you have an expression that is not well syntactically typed, you can drop down to the program logic and actually give it a type. The main difficulties here were higher order types. Doing semantic typing doing logical relation for higher order types is quite tricky. But also, interestingly, that functions are boxed. So in our case, a function is not a value, and this is a big problem because it means that the value restriction, the way to have mutable state and polymorphism, does not work anymore. So we needed a way to relax the value restriction. And if you're curious about these questions, please come talk to me. As a conclusion, so I just presented type dis, the type system for disentanglement. The key ideas were timestamp in types, which must obey the uppointer invariant. The features are type and timestamp polymorphism, subtiming, and isorecursive types. The soundness is conducted via logical relation, mechanized in ROC, Iris, and dislodge 2. And we have several case studies, so for pure algorithm. And the main case study is a deduplication algorithm with concurrent hashing. As future work, we would like to do type inference, so actually to have an algorithm generating types, and also to have existential timestamps to hide a little bit all of these timestamp binders in types. Thank you.
Thank you. So we have time for some questions. You will get a mic by one of the student volunteers.
Thank you. Beautiful work. I really enjoyed the talk. Thank you. I'm just very curious. In 2002, there was a paper by Clark and Drosopoulou on disjointness of type and effects using ownership types in an object-oriented setting with a very similar idea that the idea of the ownership should go up and not down. I'm wondering if you're aware of this work, and if so, can you compare?
So I'm not aware, but here there is no ownership involved.
That's a name. So, but the idea to
but yeah, I'm not aware of this
do the topology
uppointer
in upwards way that was there.
Yeah. Okay. I'm curious. I will look it up.
Okay. Thank you.
Thank you.
More questions? Okay, so you mechanized all this work in ROC and Iris. Did you notice, was there anything particular that you needed from Iris, or was it kind of like you do the usual approach of formalizing a logic and a logical relation in Iris, and then it all worked?
Yes, so it was a standard approach. No big modification, except for this value restriction. If you do semantic approach in Iris, you have almost bundled inside the logic that you need the value restriction. And as soon as you want to relax that, you really need to work hard.
Would you tell a bit about that?
Yeah, so I can tell it's just an issue of permuting the ghost update and the for all quantifier. You cannot do that in Iris, and we really need this similar rule for the value restriction.
So did you do the thing that has happened in some other works where you had like a pure weakest precondition and you attack the typing judgment?
So sadly, I cannot do that because my functions are allocated, so they do an effect. And I did a very ugly trick I can share with you afterwards if you want.
And now I'm very curious about that. Okay, that sounds fun. Another thing is you want to do type inference.
Yes.
Do you have any idea whether whether type checking even is decidable in the system?
So type checking should be decidable. If you annotate everything, it should be decidable. And then for type inference, this really looks like a region type system, and there was a lot of work on region type inference. So we'd like to draw some inspiration from this line of work.
Okay, that would be a good idea. Yes.
Hi, thanks for the talk. Could you go back to the slide with the rule for the parallel composition?
Yes. Here.
So is there some hidden relationship between delta 1 and delta 2 here, or can you really use any?
You really can use anything, yes. They do not matter because we are not, we know the type system gives you that delta 1 precedes the current timestamp, so you are allowed to call the function. We have very strong invariance in the type system.
I see. So you wouldn't be able to prove that it's type safe if you use some invalid thing where the return is coming before the inputs?
Yeah, no, it's not possible to do that.
Any last question before we are going to eat? Okay, I guess then let's thank all the speakers, and particularly let's thank them all for sticking so nicely to their time. And let's have lunch. And thank you all for coming.
Okay, I will try again.
Let us start. Welcome to this session on probabilistic programming, and we will start with a talk on optimizing density computation in probabilistic programs via automatic loop vectorization by Yonghyun Lim. So thank you.
Okay, hello, my name is Hyungjin Lim, and I will present about our paper named Optimizing Density Computations in Probabilistic Programs via Automatic Loop Vectorizations. So let's start with the motivation of our paper. So in probabilistic inference, calculating density from a given sample is one of the most essential operations, which is repeatedly calculated with the inference process and therefore occupies a huge portion in the total inference time. So, on the other hand, in probabilistic programming, which aims to automate probabilistic inference, density is also calculated automatically by executing probabilistic programs under density computing semantics. Let's see the examples. Here is the probabilistic model P expressed as a program. Then, if we need to calculate the log density of the model P with a given sample G, probabilistic programming framework executes model P in the density computing semantics, which calculates an intermediate densities for each sub-comment and returns the summations of all intermediate densities after the execution. So this calculation based on standard execution is simple and intuitive. However, it can be screwed up if a probabilistic model contains long loops. Usually, loops appear in a model to iterate over dataset or describe time series model. And therefore, probabilistic models in real world are likely to have long loops in their models to handle huge data sets or describe long time series data. The problem is, in standard executions, for loops with length n are executed sequentially so that they take O(n) times for n length loops. And if we use this standard execution in density calculations for real-world models, the density calculations would become costly, and it leads to the slow inference. Therefore, it is essential to vectorize loops in progressive models in real-world application. However, if a user tries to vectorize the for loops in their model, there are not much options to choose. So at first, there are only a few vectorization tools for the for loops. And each of those tools is applicable to a narrow range of loops which satisfy very strict conditions. And if the tool is used in loops which do not satisfy that condition, the calculation becomes incorrect. In this paper, we propose the novel vectorization method, which is applicable to any kinds of for loops with some advantages. First, our method guarantees correctness for any applications to loops. And second, our method is easy to implement in any tensor-based framework. And last, our method shows comparable results to other existing methods. So let's move on to the main idea of our paper. So before the main idea, let's check what language we use for log density calculations. So actually, we just use a standard imperative progressive programming language. But we exclude while statements in our language. But I think it's still expressive to describe real-world progressive models. But during the rest of the presentations, instead of mathematical notation, I will use diagrams to depict the semantics of the commands. So actually, it looks like this. So for the command in imperative processing language, the semantics gets two inputs, which one is input state and another one is given samples. And then the semantics outputs two results consisting of the output state and log density. For examples, if we execute sample command over state S with a given sample, then the result will consist of an updated S, where X is assigned to 3.2 according to the given sample, and the log density of a given sample 3.2 from the normal distribution. And moreover, since a given sample is always fixed during the full execution of the program, I will omit the diagram for the samples for depicting our ideas. Okay, then let's start with the standard execution for for loops. So in standard executions, we try to calculate the output of for loops executed over the input state S. And to calculate this, in standard executions, calculate the intermediate states and densities, which is essential to calculate the final result. So at first, start with initial state S. We obtained S0 and R0 by executing the sequence of commands consisting of assignment statement for I and body loop C. And then by using this S0, we obtained S1 by using the similar body loop. And we iterate these procedures until we get n intermediate states and n intermediate densities. And after that, we calculate the final states by just picking the last intermediate state. And then the final densities will be the summation of our intermediate densities. Then how our method work? So in our method, we optimize these loops by parallel executions. So at the goal of the execution is same. We want to get the final result by executing for loops in initial state S. But our method execute these parallelized commands are a little bit different from the standard executions. First, we will start with the initial state S, and our method makes n+1 copies of the initial state S, and then group them into a tuple of n+1 states with indices from -1 to n-1. And then our method constructs a special operator for a tuple called C parallel. This C parallel has two distinctive characteristics, and the one is it consisting of element-wise operations, and therefore it can compute in constant time with n processors. So, in a type of C parallel, C parallel gets a tuple of n+1 states as an input, and then outputs a new tuple of n+1 states. And additionally, it outputs a tuple of n densities, which are paired with states with indices 0 to n-1. And let's go back to U0. In U0, our method applies C parallel into U0 and gets a new tuple U1 with a new tuple of n densities. And then we just repeatedly apply the C parallel into each output. And if we repeat this procedure, at some point we reach the stopping point UK, where every state and the output densities looks like this, and it means UK contains every necessary information to calculate the final output for the for loops. And then we stop the iterations of application of C parallel, and then just calculate the final result and returns it as an output. So these full procedures takes OK times with n processors, since C parallel can be done in constant time with n processors. At this point, I think you might have two questions about this procedure. So one is how actually C parallel works, and the second is how can we detect UK contains the necessary information. Let's look into those questions one by one. So first, I will depict how C parallel works by simulating the first iteration and second iterations. So in first iterations, we will start with U0, and C parallel first shift these input states, which means for for each state with indices between 0 and n-1, the C parallel overlap those indices by the states with the previous indices. So for the first iterations, since every states are same to S, there is no difference between shift U0 and U0. And after that, C parallel makes a command for each state with indices between 0 and n-1 as follows, and then just execute these commands for each corresponding state, and using this, and then use the results to construct the output tuple U1. So before moving on to a second iterations, you can see that the states and densities, the output states and densities in index zeros already contains the intermediate states and intermediate densities appeared in the standard execution. And if we iterate these applications over U1 again, then we can see that now U2 contains two intermediate states and two intermediate densities in the standard executions. So we can see the patterns. U1 has one intermediate state. U2 has two intermediate states. Then we can deduce that if we iterate this procedure n times and gets un, then this un will contain every necessary intermediate states and intermediate densities in the result. So, so if we go back to the procedure I initially depict, we can say that at most n times of iterations, our algorithms can be stopped. However, can we detect the situation that UK with k smaller than n already satisfy the stop condition? The answer is yes, and our method detect this situation by comparing the current output and the previous output. So for examples, let's assume that we already iterate the procedures k times and found that the result of the k iterations is same to the result tuple in the previous steps. Then from these informations, we can deduce that UK plus 1 will be same to the result in the UK, both in states and both in densities. And this can be extended inductively until UN. And then in conclusion, we can know that UK, the value of UK is same to the UN, which is just the necessary information for every intermediate states and densities. And it means we can stop the iterations at this point and calculate the final outputs for comments. So the whole I depict the whole procedure, and we implement these whole procedures by using tensors. So we implement optimized execution by using PyTorch tensors, and we can get a powerful support of GPU operations. And then we integrate these systems into the Pyro framework, which is one of the popular PPL frameworks, and evaluate our methods based on this implementation. So in the evaluations, we try to answer two questions. So one is how our method is applicable to a broad class of models. And the question two is about the performance. So is our method faster than other existing methods? So to answer these questions, we compare our method with two baselines and with 8 benchmarks. So for the question one, we compare the applicability between three possible methods for vectorization. And as shown in the table, we can achieve vectorizations for every 8 benchmarks, but the two alternatives miss some of the benchmarks. And especially for discrete HMM, it is so specialized to a certain models, so it is only applicable to only 2 benchmarks. And then among those benchmarks, we compare the inference time between those existing methods. And then the results show that for V Markov, we dominates the method in every benchmark. But in discrete HMM, we cannot achieve the faster performance. It is because discrete HMM is so specialized and ignores many overhead occurred by the PPL framework. And in additionally, there is a 3. The table only shows five benchmarks because the rest of the three benchmarks we can so our method is only one possible vectorization tool, which is applicable to the other 3 benchmarks. Okay, so since this is just the description for our method one by one, I just decided to skip the conclusions. And if you have an interest in our papers, please tell me or talk it in the coffee break. Okay, thank you.
A question or remark? So I have a first question. So you said that you don't consider while programs, while loops, but is it difficult to generalize to while loops? I mean, you have to choose arbitrary n that is given, the parameter that is given with respect to the processor that you can run in parallel. And then does it work, your optimization? Does it work easily, or there are some issues?
Yes, thank you for the questions. So actually, Sangwon and I also considered the extension of our method to while loops. And I think it can be possible if we can dynamically allocate the processors. If we fail to reach the halting conditions within some processors, within some fixed processors. And in that case, we can double the number of the processors. So, and then we can check it. Yes, it achieves the halting conditions and so on. So.
Okay, thank you.
So on the benchmarks, there were the other ones where their methods aren't applicable, but could you compare against the, unoptimized baseline? How much speed up do you get? Like, even if you can't compare against other optimizations, do you have a sense of how much performance improvement you get?
Okay, I'm sorry. I have to turn on the computer again. So, could you repeat your question again?
Yeah, so for the 3 examples that the other optimizations don't apply to,
yes,
you could still compare your method against the unoptimized baseline.
Yes.
Do you have a sense of how much improvement you get?
So, I think I can show the full result of our experiment. So this is a full description of our Yes. So this is the full result of our experiment. So we also use unoptimized method, which we depict in sequential. And you could check that the sequential is not comparable to any other vectorization tools. And if you see the ARM and TCM and HMMs, then you could see that like our method is like maybe like 100%, 100 times better than the sequential part. So.
Okay, so we can thanks the speaker again, and we can skip to the other. So the next talk is a distinguished POPL paper. It is a talk about probabilistic concurrent reasoning in outcome logic, independence, conditioning invariance, and it will be presented by Noam Zilberstein. Thank you.
Great, thank you for the introduction. So the goals of this paper were to come up with expressive reasoning techniques for the combination of concurrency, randomization, by which I mean like discrete probability, and unbounded looping. And the applications are, there are a lot of applications in both security and also randomized distributed algorithms. For a long time, randomization has been used to do things in distributed systems that are either difficult or impossible to do deterministically. So we had a lot of ingredients to work with. The first one is concurrent separation logic, which is kind of the gold standard for compositional reasoning about concurrency. The second one is probabilistic separation logic, which is a slightly newer idea, but it's another compositional technique for reasoning about probabilistic computations. And the third one is outcome logic. So the basic idea of what we're doing in this paper is just putting these 3 things together, although it's much easier said than done. Okay, so let's start with concurrent separation logic. The kind of core piece, the core thing that concurrent separation logic gives you is this parallel composition rule, which says that if you can separate the program resources so that each thread is operating on its own portion of memory, then you can analyze the 2 threads compositionally and you don't have to worry about all the different ways that they can be interleaved. Okay, so let's think about how might we want to use this in a parallel program. Well, the most basic, randomized parallel program you might think of is just to flip 2 coins in parallel. And when we do that, we can look at each thread individually and say that in each thread, the outcomes are going to be uniformly distributed. They'll be distributed like fair coin flips. So we have some notation here. This P with the ceiling brackets just means that P occurs with probability 1, and this O plus modality allows you to bind a new logical variable that's distributed according to some distribution. And so now if we were to use the PAR rule that we saw on the previous slide to put these two specifications together, we might get something where we basically join the postconditions and preconditions with a separating conjunction. But the question is, what does this actually mean? So if we take a interpretation based on probabilistic separation logic, then the separating conjunction is not only going to mean that the state is disjoint, but also that we get some probabilistic independence guarantees. And the really nice thing about doing that is that we actually get the full joint distribution over all the program variables. So not only do we know that X is 0 with probability 1/2 and Y is 0 with probability 1/2, but we can multiply the probabilities to get the probability that both are 0, which is 1/4. So this is a nice start, but of course, the difficult and interesting part of reasoning about concurrency comes with shared state. And concurrent separation logic gives us the ability to reason about shared state using resource invariance. So we add this component I to our judgment. I is an invariant, which basically means that it's true at every step of computation. And so as long as the two threads obey this contract, they can interact with shared state. And then we have additional rules to reason about shared state. So you can allocate an invariant by basically saying, if I is true at every step of the program, then it must be true before and after the program executes. You can also use an invariant. You can open an invariant because if I is true before and after the program executes, and the program is just one atomic instruction, then I is an invariant of that program. So, I mean, these are the rules of concurrent separation logic. I haven't yet said if these are valid in our model. The first step of the paper was to basically make these rules valid in our model. But the probabilistic setting is much more complicated than the non-probabilistic setting, because you don't just have to worry about the fact that state can't be messed up by the scheduling. You have to make sure that the independence also holds. And there are a lot of ways that the independence cannot hold, right? So you can get implicit correlations that are introduced by the scheduler. Here we have an example where in the left thread, X is distributed like a coin flip, but the parameter of the coin is coming from shared state. So the scheduler can choose an interleaving where the parameter of the coin flip on the left side is dependent on Y, which is some state of the other side. So we get some correlation, and these things are not independent. So the question is, how can we have this parallel composition rule that's sound in this setting? And the solution we came up with is to use precise assertions. So if you're familiar with separation logic, the notion of precision here is exactly the same as in other separation logics. We say that an assertion is precise if and only if it has a unique smallest model. If that doesn't mean anything to you, don't worry, you can completely forget about it. The intuition of precision is that an assertion is precise if every measurable event has an exact probability. So examples of things that are precise are P in the ceiling brackets. Here, P is the measurable event, and it has probability 1, so it's precise. Saying that something is distributed like a biased coin is precise because we know exactly how likely each outcome is. And then you can join two precise assertions with a separating conjunction, and you also get something precise. But an example of something that's not precise is a coin flip where the parameter is bounded, because now we don't know the exact probabilities of each outcome. We only have a bound on the probabilities. And the PAR rule now has this additional constraint that the postcondition of both threads must be precise. And what that essentially does is it says that you can't measure the non-deterministic behavior of the scheduler. And because it's not measurable, we get independence of all the events that you can measure. So to go back to the previous example, if in the first thread we replace this assertion about X being distributed like a coin flip with a bounded parameter with something that's just true with probability 1. Now we have two precise assertions that we can put together, and the PAR rule applies. So what's going on here is that the exact value of x is not measurable. We can only measure, some probability 1 event relating to x. And so we get independence of all the events here. Okay, so the first part of this paper is, we took the rules of concurrent separation logic, we reinterpreted them in a model based on probabilistic separation logic. This was a lot harder than it may look, but we got these to work. So the next component is what additional rules do we need to actually make this logic usable? And from that, we turn to outcome logic. So outcome logic gives us rules that allow us to do case analysis on the outcome of random sampling events. Here we have we have a specification where in the precondition we're stating that the initial states are already randomly distributed. We can then reason about this pointwise, basically, for every value of x, and then put the result back under this outcome modality. So let's look at another example of how all these rules come together. Here we have a program where first we flip a coin, and then we read from that coin flip into parallel threads. The issue here is that clearly y and z are not going to be independent, because both of them are derived directly from a shared source of randomness. So the question is, how can we actually use the PAR rule to reason about this program, given that there's a clear correlation? Well, let's look at the derivation. So the first thing we're going to do is split up the sequential composition. And for the first component, it's obvious that we can just say that x is distributed like a coin flip. And now we can move on to the second component. So for the second component, the next thing we're going to do is use this outcome splitting rule to reason underneath the O+ modality. And now we're in a position where x is deterministic. It's universally quantified, but it's deterministic. The next thing we can do is move the information about x into the invariant so that we can share it between the two threads. Then we can use the parallel composition rule. And finally, we're in a position where each thread is just one atomic instruction. So we can open the invariant, and we see that in the first thread, y points to x, and in the second thread, z points to not x. So all we have to do is bubble all that information back down. And what we end up with is some sort of conditional independence assertion. So y and z are independent, conditioned on the outcome of this coin flip. And this idea sort of comes from prior probabilistic separation logics like Lilac and Bluebell, but we really need to use this case analysis rule, which was not valid in any of the prior probabilistic separation logics. So this outcome reasoning ended up being really critical here because there are a lot of different forms of compositionality, so you have to be very careful about the order in which you apply these rules. Okay, so we started with these rules at the intersection of concurrent and probabilistic separation logic. We added outcome logic, and now we have this expressive set of rules that you can use to reason about a lot of different types of programs. I want to now talk a little bit more about the meta theory behind this. So the semantics for the underlying program language here is based on a model called POM sets with formulae, which we published in Concur last year. I'm not going to get into exactly how this model works because it's very complicated, but what it gives you is this linearization model where you're basically able to take these parallel probabilistic programs and interpret them as maps from states to sets of distributions of states, where the set is the set of non-deterministic scheduler behaviors, and then for every behavior that the scheduler could have, you get a distribution of all the random behaviors that can occur. Now, like I said, the exact definition of this model is very, very complicated, but it gives us some very nice properties. So yeah, I'm not gonna go through all of these line by line, but if you glance at this, this looks a lot like the standard semantics of any kind of monadic programming language that you might expect. So the takeaway is that we had this other paper on demonic outcome logic, which was a logic for non-determinism plus probability. And essentially most of the meta theory carries over from that logic to probabilistic concurrent outcome logic because we have these nice compositional properties. But of course, you don't see any nice compositional properties here for concurrent commands because you don't get any. When you compose two threads in parallel, you can completely change their behavior. So we needed to develop completely new theory for that. And just to give you a taste, maybe I can entice you to read the paper. There were a lot of challenges. So the first one I already alluded to, we needed to tweak the measure theoretic model that we use for assertions to enable the type of case analysis that we needed to do. We had two sort of key theorems that motivated the soundness of our inference rules. The first one is invariant monotonicity. So that says that if you add an invariant, you can only increase the set of random behaviors that you're going to see. And then the soundness of the parallel composition rule essentially required us to show that the probability of any composition of two events in a parallel program is equal to the product of the probabilities of those events just by evaluating the threads on their own. There's some other issues, so we had to introduce this idea of weak frame preservation because certain types of case analysis on non-deterministic state break all the independence guarantees that you might want. So, we had to contend with that, but then we also have simple rules to get the frame rule back. And then our logic also supports reasoning about unbounded looping and almost sure termination. So this is the first probabilistic separation logic that has unbounded loops. So I will finish just by showing two examples from the paper. The first one is a concurrent shuffling algorithm. So this is based on a result from Backer et al. 2015. They showed that using a divide and conquer style algorithm, you could get up to 7 times speed up for shuffling over just doing it like the standard Fisher-Yates. So here we have an algorithm inspired by that, where we randomly partition a list into 2 segments. We shuffle each segment in parallel using Fisher-Yates, and then we concatenate the results. And we can show in our logic that the result is a uniform permutation of the original list. The one thing I want to call out here is that the independence guarantee is crucial, because if we were only able to show that L1 and L2 were uniform permutations, but they're not independent uniform permutations, we would not be able to complete the proof. So the independence is really important. Okay, we also have this von Neumann trick program. So this is a protocol for simulating a fair coin given a bias coin. But it's kind of a tweaked version where the bias of the coin is stored in shared memory and it can be altered by some adversary in another thread. So we were able to show that after this program terminates, the distribution of outcomes is, X is distributed like a fair coin. This specification also implies that the program almost surely terminates. So we have a unbounded loop here, but the loop terminates with probability 1. And the other very interesting thing about our logic as a whole is that this specification also guarantees that if you compose another thread in parallel that's altering the probability P, it can't introduce any correlation with X. So X is going to be independent of whatever local state the other thread has. So that's very interesting as well. Okay, so to sum up, I introduced probabilistic concurrent outcome logic. It's an expressive logic for reasoning about the way that outcomes are distributed in parallel probabilistic programs. We use separation logic to compositionally reason about concurrency, but the meta theory was kind of brand new and quite a bit more complicated. For future work, we're interested in looking at different scheduler assumptions. So we used a very strong notion of scheduler. We're interested in ways that we can relax that strength to reason about different types of programs using things like fairness and oblivious schedulers, where the scheduler cannot see the outcomes of coin flips. We are also interested in incorporating iris-style resources so that we can, reason about shared state in more expressive ways. And since we submitted this paper, we've actually already started formalizing some of the key theorems in Lean. So we're hoping to finish that effort. And with that, I'm happy to take questions.
Question? Yeah, thank you for the very nice talk. So, as you mentioned, some of the other probabilistic separation logics only have rules for bounded loops. Do you think your insight can be backported to those logics, or is it the fact of the abstraction model of outcome logic that has no direct translation?
So you're talking about the ones where they interpret separation as independence?
Yes.
Yeah, I think it can. I'm actually not 100% sure what the blockers were in all those cases. The theory is a bit more complicated, but I think it could be, yeah.
Hi, thanks for the talk. So you mentioned this restriction on the, if I understood correctly, the parallel composition rule that the post condition has to be precise, which sounds like it could be annoying or in the way or restrictive. So like, do you have some experience how this pans out in actual examples in terms of, like, does it prevent you from proving things you want to prove? Are there tricks you can use to get around this or something like that?
So it didn't prevent us from proving anything we wanted to prove. So I mentioned that we have this weaker type of separation that doesn't imply independence. We didn't end up developing a parallel composition rule using that, but I think you could, and then you could relax the precise thing. One thing I will say, though, is that precise, although the definition is very similar to standard separation logic, the meaning is a little bit different because kind of the granularity which you're talking about resources and stuff. So it's not really constraining anything that you could say as like a standard separation logic assertion. It's really, sorry, I couldn't hear.
Exists is not precise, I assume, on empty disjunction.
Yeah, those aren't precise, but if you put exists inside of these brackets that say with probability 1 there exists, then that is precise. So hopefully that helps a little bit.
Other questions?
Hi, great talk. Appreciate it very much. Can you spell out the validity condition that you get for the triples? For some of the examples that you...
Yeah, sure. So we're based on, this is kind of the semantic model. You have a function from states to sets of distribution of states. The triples are demonic in some sense, in that the post condition applies to every possible scheduler behavior. So when you have a triple, it's quite complicated because you have distributions, which are what you're computing over, or that's what the semantics is over. You have probability spaces, which are modeling the pre and post condition, and then you also have the frame preservation property. So if you look at the actual definition, it's quite complicated, but essentially what it's saying is if you take a distribution which satisfies the precondition and you run the program using this model, then any distribution that results, basically for all distributions in this set of results, that distribution satisfies the post condition.
Okay, thank you.
You're welcome.
Oh, there is maybe time for one short question, last question if there is. So let us thank the speaker again.
Thank you.
We have some time for the next talk, which will be remote. It will be a video. Let us wait 1 minute. Okay, so the next talk is remote. It is about probabilistic programming with vectorized programmable inference. So,
hi everyone, my name is McCoy Becker. I'm a student at MIT's Probabilistic Computing Project advised by Vikash Mansinka, and today I'll be presenting a language designed towards faster, more parallel, programmable probabilistic inference. Probabilistic programming languages aim to support practitioners of probabilistic modeling and inference. These systems provide automation to help users write and work with probability distributions. One key operation in probabilistic modeling is conditioning a probability distribution, an operation fundamental to Bayesian inference, a model of reasoning that is commonly used in machine learning and reasoning under uncertainty. To support computing with conditional distributions, probabilistic programming languages provide two key capabilities. The first capability is the ability to describe joint probability distributions, which probabilistic programming languages automate by providing expressive modeling languages. Using these modeling languages, users can write down probability distributions as programs, which often make use of programmatic components like 3D renders, symbolic planners, or program interpreters as part of their definition. The second capability PPLs provide is inference libraries, an automation to support the programming of inference algorithms. These algorithms are programs designed to compute or produce approximations to the conditional distributions induced on the programs written in the modeling languages when we condition those programs on data. Now, in this talk, I'll be presenting a design towards vectorizing the modeling and inference stack for probabilistic programming languages, granting access to good performance and scaling via parallelization. Our concern in this talk is exploiting embarrassingly parallel subroutines in programmable inference. Programmable inference is a paradigm for probabilistic programming languages where users are allowed to customize their inference algorithms, often with degrees of freedom which themselves are programs. Take importance sampling as an example. Importance sampling is an approximate inference algorithm which involves a guess and check style pattern, where guesses from one distribution are used to approximate another typically intractable distribution. Here, the target, the imagined intractable distribution, is shown in orange. The programmable inference part is a proposal distribution, which is called proposal in each of the code snippets. This is a programmatic component which is sampled within importance sampling to produce the guesses. These samples are shown in blue on the left-hand side and green on the right-hand side. The samples are scored using a quantity called an importance weight, a density ratio between the proposal distribution and the target. In many probabilistic programming languages, importance sampling is written as a sequential program, shown on the left-hand side of the animation. Samples are drawn from the proposal and weighed in a for loop. But both the sampling process and the weighing process perform the same computation in each iteration of the loop. If we could execute this process in parallel, we could produce many samples simultaneously and then weigh them all at the same time. This is shown on the right-hand side. On modern GPU devices, this drastically improves the scaling of this process as the number of samples increases, a useful way to improve the approximation quality of importance sampling. Our design allows users to do exactly that and take advantage of other opportunities for parallelism in programmable inference. We do this by exposing a vectorization transformation called VMAP, which composes with probabilistic automation used to write programmable inference algorithms. Vectorization in this context means transforming computations over scalar data or array data to operate on higher ranked arrays. In particular, VMAP stands for vectorizing map, applying a function over some axis of array arguments. In our language design, VMAP can be applied anywhere in probabilistic programming code. It can be applied to probabilistic programs which are used as models, allowing us to make use of idioms such as independent and identically distributed random variables, as well as repeated invocation of other probabilistic programs as submodels in our modeling toolkit. VMAP can also be applied with an inference to support repeated sampling idioms like multiple guesses in importance sampling, as we just saw, but also enumeration patterns. Enumeration is a high-quality inference strategy which is expensive in traditional PPLs which implement it using a for loop, but becomes cheap when vectorization is automated. Overall, our work contributes a compiler for our design which integrates with the JAX array programming environment, a formal model characterizing how our design works, and an empirical evaluation including micro-benchmarks and 2 case studies. Before walking through how our design works, I want to give a short and quick practical survey of the applications of our work. Our system can be used to support probabilistic modeling applications like robot localization. We'll see more about this example near the end of the talk. But quickly here, a robot traverses a 2D geometry world and we get noisy measurements of its position. The goal is to infer the trajectory of the robot. A particularly good programmable inference algorithm class for this type of problem is sequential Monte Carlo, and our system is set up in such a way that we can support several various vectorized versions of this algorithm. In addition, because the implementation of our language and compiler makes use of JAX, a robust and mature machine learning framework, we benefit from great automatic differentiation support, allowing our system to support fast vectorizable Hamiltonian Monte Carlo, a technique commonly used in statistics in PPLs like STAN and NumPyro. Finally, vectorization can be used to take advantage of modeling structure like conditional independence. Our system can be used to exploit conditional independence to parallelize high-dimensional inference problems, drastically reducing the time it takes to execute the inference processes. For instance, we perform approximate probabilistic inversion in a noisy version of Conway's Game of Life for a 512 by 512 game board in milliseconds on a consumer-grade GPU device. Now, for the next part of the talk, I want to give intuition for our design and system works. And quickly, I'll just say that our paper contains a formalization of the intuitive presentation, which I'll give now, with a formal calculus, denotational semantics, and correctness theorems, along with logical relations arguments. I'd refer interested viewers to our paper for the details of our formal exposition. But for the rest of the talk, the examples I will use the syntax of our compiler implementation. The syntax is Python code, and our compiler works by exposing a DSL in Python to users, which allowed them to write our system's probabilistic program type, a type called generative functions. Generative functions are used to denote probabilistic models in our system, and a few things to note about the syntax of generative functions. First is the @gen decorator that you see on lines 2 and 10 above the Python functions denotes that the function is a generative function. Now, within one of these generative functions, users can introduce random choices by invoking distributions, and even other generative functions by using the addressing notation, where the addresses are shown in green in the code snippet on the left-hand side. Here in polynomial, for instance, on lines 2 through 7, we define a model over the coefficients of polynomial curves. Each coefficient is drawn from a standard normal distribution. Now, the design of generative functions is compositional. We can use the polynomial program inside of another generative function point to define a bigger distribution over curves and point data. Now, given one of these generative function objects, how can we compute with them? What can we do with it? Our design gives users access to interfaces for probabilistic computation. These interfaces, called the generative function interface, cover concerns like sampling, density evaluation, updating of an existing sample. There are other interfaces as well, which you can see in our full paper. So one applies these interfaces to generative functions to construct probabilistic computations. One can use these interfaces to implement inference algorithms. Take importance sampling again, for instance. Programmable inference algorithms often involve logic that requires sampling from one generative function and evaluating the density of another. Here we sample from a proposal using Simulate, which gives us an object called a trace. A trace is a structured sample from a generative function, which I'll talk about in the next few slides. We then use the trace to we then take the trace and evaluate the density of the model generative function at the trace using the assess interface to compute the importance weight for importance sampling. Remember, this is the guess and check strategy for approximating the distribution of model that we saw earlier in the talk. Now let's dig in a bit more and get a bit more intuition for Simulate and how it works. Simulate samples a trace from the distribution which the generative function denotes, and at the same time computes the evaluation of a density function for the generative function at the sampled trace. Traces in our system hold tree-structured data with addresses and the values of samples along with that density evaluation. The addresses in a trace can be read off from the syntax of the generative function. On the right-hand side, for instance, the point generative function has curve and obs as addresses, and the curve address denotes the invocation of the polynomial generative function, which itself has a, b, and c as addresses. The result of applying Simulate to the point generative function is the trace structured on the left-hand side, this hierarchical tree structured object. But just to make it clear, in our point model, a trace represents a curve and a single point sample and a density evaluation. That's all, even though the object has this structured hierarchy. This is what it's representing, a distribution over the data on the left-hand side. So then how are probabilistic interfaces like Simulate implemented in our system? Well, they're program transformations. Our compiler takes the source code of the generative function and constructs a transformed representation that accumulates the samples and density values required to implement the semantics of Simulate. You can see our paper for a detailed description of how this works, but on the right-hand side we show the first-order representation that our compiler outputs. It consists of sampling statements, array primitives, density evaluation statements. And this same type of structure is true for all of our other probabilistic interfaces. They're all implemented as program transformations. Vectorization also works as a program transformation. It's a trace structure preserving program transformation on the representation I just showed you. The real work of vectorization is done at the primitives of our language. All primitives have built-in vectorized versions. Each primitive has a rule for how vectorization under the VMAP transformation transforms it to operate on higher ranked values. Practically, this means that under VMAP, computations which produce traces create the same structure, the same address structure, but with vectorized leaf values. Here, for instance, you can see that under VMAP, the obs value might be inflated from a scalar to a length 5 vector of floats, depending on how the user wishes to use the VMAP transformation. So these interfaces, the probabilistic interfaces and our VMAP vectorization interface, give us a model of programmable inference and user-directed vectorization. How does vectorization look in our syntax for our users? Say we want to write a regression model where we define a distribution over multiple points, all drawn noisily from the same curve, the same polynomial, but at different values on the x-axis, which are passed in as arguments to the generative function on line 19. This is the x's argument. To start, we change the signature of our point generative function to accept the coefficients of the polynomial curve as arguments. And then on line 22, we apply VMAP to the generative function. We make use of a keyword argument here called argsMapped, which specifies that VMAP should be applied over the first argument, that x is the values of the independent variable that we're passing in. Using VMAP and that argsMapped keyword argument, we specify that we're mapping over the input x's. We get multiple values for the independent variable. This induces a model which maps over the input x values, a vector of x values, and samples a point for each one. It's a bit easier to understand this visually. If we simulate from the endpoint curve program, that thing that we just defined, we get a trace which represents the type of data that's shown on the left-hand side, a curve and multiple points. This is starting to look like a distribution that could be used for regression. The trace, which includes the random choices and addresses, looks like the right-hand side. It's the same structure as the original trace we started with, the same address structure. But note that OBS, which before contained a single scalar random choice, now includes 5 draws for each point. Now, we created that endpoint curve program by applying VMAP inside a generative function. We used VMAP as a modeling idiom. We applied it to point, another generative function. But our design also allows us to apply VMAP to the result of applying simulate itself. Here on this slide, we VMAP the application of simulate to our endpoint curve program. Right. So now this is an example of nesting of the VMAP transformation. This returns a trace with the same random choice structure as the original, which here we've called traces to indicate that it corresponds to multiple samples from the endpoint curve generative function. Oh, and here we're making use of another keyword argument, repeat, that just means IID samples from the probabilistic computation. Because vectorization is trace structure preserving, nesting of vectorization is handled automatically. What we saw on the previous slides and shown on the left-hand side, when we VMAP the point generative function and apply it over, say, 5x values, we inflate the rank and shape of the OBS random choices, the OBS random choice to an array with length 5. Then on the right-hand side, I'm showing what we just did on the previous slide. When we VMAP the application of the simulate interface, the sampling process itself, we get multiple independent samples from that distribution. And I'm showing 3 of those samples on the right-hand side. Note that the coefficient random choices in the vectorized trace from vectorized model have changed rank and shape. And so has the OBS random choice, up to an array of size 3, 5 now. In addition, the density for the density is now a vector, each element corresponding to a density evaluation on each of the independent samples. This slide gives intuition for how repeated application or nesting of vectorization works in our system, nesting of our VMAP transformation. So that gives a sense of how our system works. We have these probabilistic and vectorization interfaces. But then with these interfaces, one can construct interesting programmable inference algorithms. Here on the left-hand side, I'm showing custom proposal importance sampling, where default proposal is itself a probabilistic program. This is just the same importance sampling recipe that I showed before, expanded out a bit. Now, the thing to note here is that this is a single particle version of importance sampling. But by using VMAP, we get a multiple particle version for free, in a sense. On the right-hand side, we're free to apply VMAP to the single particle version, and we get out a multiple particle version using the VMAP transformation. And the big payoff here is that the big payoff of vectorization here is utilization of parallel hardware to scale algorithms like the one shown on the previous slide and other inference programs. For instance, we might be using our polynomial regression model to infer curves given data, which is shown at the bottom. Using our system gives the user access to GPU execution, and the scaling becomes close to constant until the GPU memory is fully saturated. In the top left figure, we're showing the scaling as we increase the number of guesses in importance sampling. In the top right figure, we're showing the log marginal likelihood estimate computed from the importance weights. This is an estimate of the probability of the data and is used as an informal intuition for goodness of the approximation. Within our language, it is easy to scale inference algorithms, inference programs in embarrassingly parallel directions using VMAP. Now, we implement a compiler for our language called GenJAX. Our compiler is embedded in Python, builds on top of JAX, and uses program tracing to lower Python functions to a first-order IR. We saw this when I was discussing how simulate and our other probabilistic interfaces are implemented. Program tracing allows us to partially evaluate away our high-level program transformation automation, and we're left with pure vectorized code in JAX, which can be further compiled with state-of-the-art compilers like XLA to run on GPUs and other pieces of parallel hardware. Moreover, because we closely integrate with JAX, our system can make usage of all of JAX's existing automation, including AD, automatic differentiation for algorithms such as Hamiltonian Monte Carlo. We benchmarked our compiler implementation and found that it is competitive with hand-coded JAX while retaining the benefits of our high-level automation on several modeling and inference tasks using importance sampling and Hamiltonian Monte Carlo. We also explored the capabilities of our system on several examples, several example case studies. One example involves approximately inverting Conway's game of life using Gibbs sampling. The rules of the game of life are shown here. The transition function defines simple evolution rules for what pixels are turned on and off in the board state, given the state of their neighbors. The question here is, given an observed state, determine a preceding state that evolves to generate the observed state. The state space here is huge. For a 512 by 512 board, the number is quite a bit more than the atoms in the universe. We can set up a probabilistic model version of the game of life using generative functions and approximately invert it using inference. A key observation for this problem is that the posterior in the model, given a fixed target state of the game of life, can be factorized due to conditional independence due to the transition function. A good strategy here is to sweep across the board by breaking it into pixels with windows which are isolated from one another, flipping those pixels by sampling from each of those local factorized posteriors and repeating the process. This is a Gibbs sampling algorithm, and vectorization allows us to compute the flips for all the windows in parallel. Applying this technique allows us to discover approximate inversions in milliseconds on a GPU, even for a large 512 by 512 board. Another example involves constructing a toy problem in robotics. A robot traverses a world and gets noisy LiDAR-like measurements of its surroundings. If the map is known, can we infer where the robot is within the map? To solve the inference problem in this example, we use a programmable inference algorithm class called sequential Monte Carlo. Sequential Monte Carlo produces a particle approximation to the location of the robot, seen in shaded green and yellow. The standard variant of the algorithm, which is shown on the far left, uses the prior of the model as a proposal. In this case, the prior is random walking with Gaussian noise. This fails to accurately localize the robot, as you can see on the far left side. But there are many variants of SMC. A common technique used to improve the algorithm is to apply MCMC inference moves to the particles at each time step. This is shown in green in the middle, where we use HMC moves to try and improve the approximation. Now, it improves the performance over blue, but loses track of the robot in the middle. A final strategy is to use a custom proposal as a guesser. So instead of using the default proposal, we use a custom one, another program, another generative function as the proposal. On the right-hand side, we make usage of vectorization to enumerate a grid near the current latent position. This grid is weighed according to the observed likelihood of the data, and the maximum on the grid is chosen. From that maximum, we then sample from a 2D normal to guess the next latent position. This strategy is highly efficient and makes usage of vectorization in 2 dimensions, vectorization over particles as well as vectorization over grid points. So this is an example of a nested VMAP in inference. Now this variant ends up being the most accurate and the fastest, approximately 2 milliseconds to track the robot accurately over 16 time steps. Now, in conclusion, we've discussed our work on a compositional approach to vectorization of programmable inference. We refer interested viewers to our paper where we give a careful treatment of our formal model and discuss other features of our system not covered in this talk. Thank you for your time. The QR code on this slide provides a link to our system implementation and POPL artifact, and please send any questions to my email. Thank you again.
So, since it is remote, there is no questions session. You can send an email to the speaker. I can ask to the next speaker to come. And we have 2 minutes break.
It's just me. Sorry? Can I? Yes, it's okay.
So the next speaker is Davide Barbarossa. This is the last talk of the session, and he will speak about tropical geometry of probabilistic programming languages. But probably we have to wait to have the slides on the main screen.
We can wait. Is this fine? Everyone can hear me and can see good? Perfect. Okay. Well, hello everyone. I'm Davide Barbarossa. This is a joint work that I did with Paolo Pistone, which is sitting somewhere over there. So the two keywords are, as you can see, probabilistic programming languages, of course, and tropical geometry. Let me start by the first one. Let's start by probabilistic, like graphical models. Okay, so for example, here is one. So we have a certain number of random variables, those are those nodes. Maybe those two here are observable ones, and then we may be interested in all the possible trajectories that lead to these observable variables. We can ask typical basic statistical inference questions, like, for example, what's the probability of reaching a fixed outcome, or for a given observable, what are the trajectories which have maximal probability that reach that outcome. Now, on the side of programming languages, we can, of course, also specify models via programs, of course. For example, let's take this program here. So you can see there are some booleans, there are some lambdas, so this is based on the lambda calculus, so we consider a high-order functional language. And this plus with the subscript is the only probabilistic feature of the language. It's a very simple one. It's just a biased coin tossing. So it goes left with probability x and goes right with probability, the complementary of x, 1 minus x. If you would execute this language for example, in a call by name reduction strategy, you would see that, well, you have to perform n coin flippings, and if you record all the possible branchings that you can take, you would end up with a model which looks like this, like the previous one. I'm using this x bar in order to indicate the complementary of x. And here, of course, the interesting part is that the typical questions that we could ask before on graphical models now become questions about the computational behavior of our program. So, for example, we can ask what's the probability that the program computes true? Or, given that the program has computed true, what are the reductions which have highest probability? These kind of simple questions. Now, okay, you don't need to understand exactly this program, it's just to show it to you. But if you consider this M, what's interesting here is that since we can exploit all the expressiveness of the language. Here we have a fixed point, so there is some recursion going on, and this would correspond to a model which starts by an initial distribution D, then updates it, then makes an observation on it, and depending on the outcome, it may continue or return. And you see that this is in general, it's an infinitary model. This is just a finite portion of it. What's interesting here is that, of course, usually, finite models are the ones which are maybe most solid, or at least are most simple, while from the point of view of programs, we immediately have a very large complexity, even in very simple cases like the one that we consider. Great. So now for the second one, for tropical geometry. Let me introduce this with a similar example to the previous one. So again, we flip n times a coin, and then we always return true. Well, of course, the probability of returning true is 1, but how can we compute it? Well, we can take all the possible reductions of this program, and maybe here it's a good moment to remark that when I consider these biases of the coins, so here it's, for example, a probability x1, well, actually, I don't want to look at it as a number, as a probability, but I want to look at it as a formal parameter, okay? So here, for example, you see I'm using x bar now. This is, again, a formal parameter, and the act of actual instantiating this with actual numbers, probabilities, will come after if needed. So if I take all the possible branches, this would give, well, a product of all these probabilities, and now it will give just a monomial, and I sum all of them up. If you think about it, this is the same as this big product here. And that's great. But now let me consider another question, like what is the maximal probability? So I want to compute this maximum. And let me make this trick. I apply a minus log in front of everything. Now minus log is a strictly decreasing function. So it goes inside and changes max into mean. And now I have this. I have the minus log of a product, of a monomial, and this is the sum of the minus log. So I have these new variables z, which are the minus log of the x. And okay, this is easily seen to be this. And what's interesting here is that if you look at these two pink expressions, they look different. But if I actually read the top one and I read, instead of multiplication, I read plus, and instead of plus, I read minimum, then the two expressions become the same one. Okay, and this passage is precisely what's the idea behind tropicalization. It's precisely moving from, for example, the 0-1 interval of probabilities with sum and multiplication as operations to, well, its minus log version, which in this case is the non-negative real numbers. With operations which are now minimum and plus, and this becomes a semi-ring, and it's what it's called the. I mean, it was one of the possible choices for a tropical semi-ring. Okay, so I mean, you see that this idea of tropical numbers is related with optimization problems in general, but why it's interesting, it's relevant for any kind of statistical inference. Let me illustrate this again with another example. So consider these two different formal polynomials. And now let us tropicalize them. So I read plus, when I read plus, I read minimum, and when I read product, I read plus. I'm consciously neglecting the coefficients here, the 4, the 6, and the 4. Now I have these two expressions, and if I imagine of now actually instantiating these parameters, x and x bar, with actual tropical numbers, so non-negative real numbers, well, you can easily convince yourself that now these two expressions evaluate to exactly the same thing, okay? And this is why we introduce this notion of tropicalization, which takes a formal polynomial, or in general a formal power series, which is just a formal polynomial with potentially an infinite number of monomials, and evaluates it tropically, so on tropical numbers, and considers it as an actual function. And the point here is that when we make this tropicalization operation, you see that we need to compute a minimum, but we don't need to explore all the possible monomials that are there in order to compute the minimum. We maybe just a small subset of them, it's enough. For example, this polynomial up here corresponds to all the reductions of this program at the bottom to true, and the fact that that this minimum actually shrinks to the minimum only on two monomials corresponds to the fact that the maximum probabilities of this program returning true are achieved by either going always left, so always taking heads, or going 3 times right, or 4 times. It's 4 calls. Okay, now there is another very elegant way of telling the same story, which is really at the heart of tropical geometry, which is obtained by considering this Newton polytope. So if we consider a polynomial S here, so it's a sum of monomials, let's forget again about the coefficients, but if I only look at the exponents of each monomial, then those are, integer coordinates in a n-dimensional Euclidean space. So we have all these points, and we can take the convex hull of all of them, and we get a solid, or in general what's called a polytope, and this is what's called the Newton polytope of the polynomial, and maybe it looks something like that. And actually, we are interested in the vertices of this object. So the vertices are, of course, this point here. Now, the reason why we are interested in the vertices, we can see it from this example. So if I have this polynomial here, if I expand it, it's this big sum. Now, if I consider for each monomial the corresponding point, I have these 6 points, which are the points here. And if I take the convex hull, of course, I get the 2 simplex in gray. But you see that actually the vertices of that, it's not all the 6 points, it's just the 3 vertices of the triangle, right? So those are the vertices, and if I write it as a polynomial, it would correspond to this much smaller polynomial here. And this precisely corresponds to the idea that I mentioned before about of shrinking the number of monomials to consider when we have to compute a minimum, to shrink it down to a smaller set. Well, actually, for our purposes, we needed to introduce a minimal version of this Newton polytope. It's not really important for the purpose of this talk, but just to give the idea, instead of taking all the vertices, we just take the minimal vertices, where minimal is with respect to the pointwise order on the coordinates. And for example, this is an example here. If we consider this polynomial, then the Newton polytope would be this pink, purple, maybe triangle. But you see that this vertex here at the top right is not minimal. So when we consider the minimal Newton polytope, we kill also this point, and so we shrink even more the number of points that we are considering, which correspond to the monomials. Great. So now, all these things, of course, are very well known, and we didn't, invent all of those. And in fact, there are already previous works that use tropical geometry based on these ideas, and of course, developing on that for statistical inference typically on Bayesian networks or finite graphical models. So here there is a reference. And the reason is that this Newton polytope can be computed efficiently from the starting polynomial. And to consider this Newton polytope, it's interesting because the vertices of it, as I already said, reduce the space of possible solutions to some optimization problem. And this optimization problem may be things like computing the most likely explanation to some probabilistic model. Now, but this is typically on Bayesian networks and on these kind of models. So our question in our paper was, can we import from all this tropical geometry studies, can we import some of these tools in the world of programming language theory in order to design some programming language oriented methods that would at least express these questions and directly on the programming language, because in this case, there is no substantial distinction between a program which has a finitary behavior or an infinitary behavior, in the sense that we have, that's the whole point of programming language theory, to have a toolbox of tools which work compositionally on the whole program. And in this case, we take high order functional languages, and so we have a lot of theory in that direction. So the 2 points that we want to address is, can we define with these compositional tools the Newton polytope, or actually the minimal Newton polytope for a program, and can we estimate it, can we compute it, or maybe not? So first of the 2 questions, when we think of compositional tools, well, typically we think of categorical or denotational semantics. And there is a very well known, very well studied model of these kind of languages that we consider. So lambda calculi extended with even just one very simple probabilistic feature, just a coin flip, parametric here. And so there are a lot of studies in the denotational models of these kind of languages. And the one which is related with what we do, we really use its properties, is this, which is called weighted relational model. So just the idea is to interpret a type as a set of formal elements, of indices or variables, and a term can be seen as can be interpreted as with something which can be seen as a formal power series, or actually a family of formal power series. and the coefficients are chosen in some fixed semi-ring. Now, by choosing in a clever way the semi-ring of coefficients, we can have indeed a model for the language that we consider. And in order to do this, we need to consider as coefficients formal power series themselves, where the variables are the parameters of the program, which means the biases of the coins that we use in our language. Actually, it is already like complex enough to look at closed terms of type bool, and in this case, the interpretation would just give two formal power series, one corresponding to the output true and one to the output false. And those basically collect all the possible reductions to the corresponding output and collect them all together as each of them as a monomial. For example, let's see this very simple case here. We make 4 coin flips as before. And if you would compute the denotation of this program compositionally, then this would give this polynomial here, which precisely corresponds to all the possible branchings in the reduction of the program. You see, we can go we have to make 4 times a choice between going left or right. But again, these tools are well defined for any kind of program, even for programs which have an infinitary behavior. For example, here we have a fixed point, so it's a recursion which is there, and this program corresponds to the experiment of flipping a coin until we find a heads, for example. In that case, we return true. And so we can compute the denotation of this program, and this would give this power series. Now you see that it's an infinite series, and this precisely corresponds to all the possible reductions of this program to true, and you can see it because maybe we find heads at the first iteration, so we only have to go right, so x bar, or maybe we find it at the second one, so we have to go 1 time left and then right, or 2 times left and 1 right, and so on. So now, with this in mind, we can start to think about basically what's the basic idea behind our paper, which makes everything work in a sense, which is this finitary claim about closed terms of type bool, and it says that for each of those there is a finite set, and this is a set of reductions, okay, and this finite set is such that for all assignment of probabilities to the parameters, in that finite set, we can always find a most likely reduction. Okay, so it shrinks it gives a finite set of possible reductions to consider in order to find the most likely one. Or equivalently, there is a number which is an upper bound on the choices on the probabilistic choices that we have to make before finding such a likely reduction, most likely reduction. Now, we can make this more rigorous, and actually this follows from this theorem here that we proved on formal power series. If their coefficients are on a discrete set, then when we tropicalize them, so when we consider them as actual functions on tropical numbers, then every formal power series, when tropicalized, coincides to a polynomial, okay? So there is a polynomial which makes this infinitary object, like a formal power series, collapse to a finitary one, like a polynomial. And with this, we can define a number associated with a program, which we call the tropical degree, and this is just the smallest degree of one such polynomial, which makes the power series associated to the interpretation of the program, as I defined before, collapse to a polynomial. Or equivalently, we can take the Newton polytope associated to this polynomial, and this I think that is very nice. We can associate this geometric figure to a program with this idea of minimal Newton polytope actually. Now there is a drawback here, which is that actually the problem of knowing if the tropical degree of a given program is a given number, this is an undecidable problem. So we have to cope with this. Anyway, so this checks the first point, because at least we can define it in terms purely program theoretic and compositional. Now, for the second question, well, we know that this Newton polytope is not constructible, right, in a constructive sense, because it's undecidable. But maybe we can develop some framework in which at least it makes sense to estimate it in some way. And this framework, we find it in what are called non-idempotent intersection types. Those also are very well studied in the literature on lambda calculus and this kind of languages. And so the idea is that now we have judgments like this, and we want to build derivation trees. And a judgment consists in having, in the context, a certain number of resources which limit the usage that the program can do to the inputs, and then we have a fixed output for the program. And in our case, we label every of those judgments with this small s, which is a polynomial, again in the variables which are the parameters of the language. And the idea is that each monomial of this polynomial here records a reduction of the program, which has been explored in the derivation that we are building. And here there is a trade-off to take care of, because, well, on the one hand, of course, we want to make this polynomial as small as possible, because we want this to be, at least in principle, feasible. But also we want to, at least we hope, to be able to find inside this polynomial, which is generated by this typing derivation, we want to find a most likely reduction inside. So we need to explore enough reductions, right? So there is this trade-off. And the way that we do this is by comparing different reductions at the same time. So the typing judgments actually contain multiple derivations at the same time, and they are a bit complex, so I'm not showing to you the full system. If you want, I can discuss it in the questions. But I just want to show quickly the application case. So this is how it would look like in the usual intersection type case. So in our case, we have multiple of those in parallel. This is just one of them. And for us, we also have to label with polynomials. So here we go. So remember, here as 0 is the reductions. You can think this really as the set of reductions that we have explored in this derivation for n. Here is a set of reductions that we have explored for n1, and so on. And when we apply the calling program to its argument, we need to take care of all the possible concatenations of these reductions, basically. And this actually corresponds to taking the product of the polynomials here. But there is a problem already that you can see, because when the number of application grows, well, this multiplication of polynomials can become easily intractable. So we need to to keep this small as well. And we do this by relying on the literature in tropical geometry, with which we were able to show that there is an algorithm for computing multiplication, which we call Viterbi-Newton multiplication, which takes a finite number of polynomials, and it gives not really the product of all of them, but just the minimal polynomial of the product. Minimal in the same sense of the minimal Newton polytope that I showed you before. And this is now feasible, and this is precisely what we use in each instance of each rule of the derivation in the typing system. So you see that every time that we need to compute products, this will appear also in many other rules, not just the application one. And here we call this optimized products. That's great. Okay, here is an example. I mean, you don't need to understand it again. It's just to show a very simple derivation. And so this is showing that for this program, so we make 3 coin flips and then we return true for the only possible output in this case, which is true. This derivation has explored this set of 2 reductions. Either we go 3 times left, either 3 times right, and you see that it did it by precisely using this Viterbi-Newton multiplication, because at a certain point we needed to compute this product, but instead of computing all the, well, in this case just 4 monomials, we just kept the minimal ones. So that's great. This system, we showed that it is sound with respect to the weighted relational model that I mentioned you before, and it's also complete in a specific restricted sense. But that's precisely it's good. That's precisely what we want, what we expect from these kind of typing systems. And it's also, we could show that it's also complete for the problem of finding the minimal Newton polytope. So for every closed program of type bool, there exists a derivation in our system that generates the polynomial corresponding to the minimal Newton polytope of the program, and therefore also that gives us the tropical degree. So that's great. We are happy, because if we have this derivation, then we can also solve the basic inference task problems. For example, we can trace back the associated maximum maximal reductions from the minimal Newton polytope, or for each given vertex of this geometric figure, the vertex corresponds to a reduction of the program, and by standard tools from linear optimization, we can find an assignment of probabilities to the parameters that make that particular reduction the most likely explanation, for example. Okay, so we are happy, but of course there's a problem here, which is that the problem already of finding the tropical degree is undecidable, right? So we cannot construct this. But that's not the end of the story, even if it's very quickly the end of my talk. It's not the end of the story, because still the fact that we could design these tools, which again are compositional, are perfectly like in the line with the research in programming language theory, allows us to, at least in principle, design a proof search strategy, proof search on these typing derivations, which of course will be complete in the sense that it finds the correct polynomial, but we don't know, we cannot check when it happens. So from the outside of the system, the user has to decide when to stop. And this is the most important perspective that we have to actually implement this and to study the efficiency of this in practice. And then there are also some other possible other perspectives that I leave here for you to read. Thank you.
So maybe time for just one quick question or remark. So I have just one. At a certain point, you have said that you are computing, when you move to the tropical interpretation, you are computing the most likely reduction sequence for getting a result. Do you have an idea if this can be characterized by a strategy, an operational strategy, which is independent from the term, but just?
I don't know. I mean, in that case, the fact of I don't know. I should think about this, but I mean, in that case, the point of finding the reduction with highest probability really comes from the fact of considering this minimum, right, of moving to the tropical one. So it's a completely different, like disjoint reason why this happens than like a reduction strategy reason. So I don't know, but that's, yeah, that could be, I don't know.
So thank you. So I think so we can thanks the speaker again.
Thank you.
And this is the last. This is the last talk of this session.
Of POPL. So the session is called Automata 2. I'd like to instead call it Automata, Decidability, and Algorithms. The first speaker is Alexis de Colnay, who is going to talk about counting and sampling in trace regular languages.
Oh, good, my slides are here. Go. Okay, so yeah, so right, so I'm going to present our work because Umang is also a co-author at that work as well as Kuldeep, who is not here. So the first thing, these symbols R means that the author ordering is randomized. Now this talk is about two counting problems. So in a counting problem, you want to determine the size of a set, which is given to you in some form. So the first problem that I'm going to mention a lot is called sharp NFA. So this sharp is the symbol we use to denote counting problems usually. So here you are given an automaton, non-deterministic finite automaton, NFA, and you're given a certain natural number n, and you want to know how many words of length n are accepted by the automaton. But we are really more interested in an extension of it, which I will denote like this, and I will read it, sharp NFA modulo equivalence. I will try to refer to this as counting the traces of the automaton, and I will define in a minute what I mean by traces. I'm going to have to introduce quite a lot of stuff before I can state the main result, but I thought I would state them already here. We have positive results. This is theoretical work, but we still have positive results. We have polytime algorithm. The first one is allowing us to do approximate counting. We can approximately count in polytime the number of traces that intersect a certain slice of the automaton language. And the second result is that we have also a polytime algorithm to do almost uniform sampling of traces. Now, what are these traces I'm talking about? So the idea is that the automaton is going to accept words, but we have something that tells us that some words, although they are different, they are in fact, they look different, but they are equivalent. They represent the same thing. This is formalized using a notion of independence relation. So we have a fixed alphabet, a finite alphabet sigma, and we'll have an independence relation over letters. This is set I. So what it means is that when you have a word and you have two letters A and B that are independent of each other, so you have that A, B is in this set I, then you can swap them if they appear consecutively in a word. So this word here, if A and B appears consecutively, I can swap them and I obtain this new word. And these two words, I say they are equivalent. Okay, so this is this equivalence relation tilde here. So just to be clear, I is a relation on letters. Tilde is a relation on words. And I insist it's important that the words be consecutive, otherwise you are not allowed to swap them. And what I call traces are equivalence classes for this relation. So an easy example, here you have three letters, A, B, C, and this is your independence relation. This is saying that you can swap A and B here. So if you can swap A and B, we assume you can also swap B and A. So if this thing is a symmetry, so you have AB, you have BA. And you can also swap B and C. And if you look at this word, then this is equivalent, so then I can swap A and B, it gives me that. I can swap A with the second B, it gives me this. I cannot swap A and C, but I can start from scratch and swap B and C, and so on and so forth. And the trace is this. This is this set of words, this is this equivalent class. So some examples of words that are not equivalent. These two words are not equivalent because I cannot swap A and C. Not possible, so if A is right and C left, there will be no equivalent word where this is reversed. And also, I cannot just change a letter into a new letter, or add new letters, or remove letters, so yeah. There are some degenerate cases. For instance, if no letters can be swapped, then this independence relation is empty, and so two words are equivalent if and only if they are the same. That stands to reason. On the other hand of the spectrum, you have the case where everything can permute, everything can be swapped, and now two words are equivalent if and only if they are anagrams, like parrot is the same as a raptor, and a dormitory is the same as a dirty room, which is good because I'm presenting in the NEF. Now, these are the problems that I've stated informally before. Now here is the correct version. Counting words. Here, so you are given your NFA, your automaton, you're given a certain integer n. You want to know how many words of length n are accepted. So this is the size of the nth slice of the automaton. Counting traces, you're given the same thing, but you also have this independence relation. Some words are now equivalent to each other, and you want to know how many traces will intersect this nth slice of the automaton. So how many traces contain at least one word that is accepted by the automaton. So one last example before we start diving into the result. That's an NFA. Oops. Same three letters as before, same independence relation as before, and we look at words of length 3. So, and I've listed here all the equivalence classes. Each row here is an equivalence class. So you see that some equivalence classes contain a single word, other contains a bit more. So if I were to ask, okay, how many solves the sharp NFA problem here, the answer would, for n equals 3, the answer would be 5. There are 5 words here that are accepted, of length 3 accepted by this automaton. Usually it's not so easy to find them, but in this case, since it's a tiny example, you can do it. But how many traces would intersect the language here? Well, you have 4 of them. These 5 words, they intersect 4 traces, 4 equivalence class that are listed here. So the answer to the sharp NFA modulo equivalence problem here is 4. All right, that I will ignore. Now, so why are these problems interesting? So first, they are fundamental problems, and also they have many applications. So I've put here an example with model checking. So on the high-level idea is that if you're doing model checking, you may want your model checker will have to enumerate strings that correspond to execution of programs. But your programs, you can see them as automaton, and how efficient will be your model checker? What will be the cost? Well, if your model checker is enumerating, is taking some fixed time to enumerate a string execution, which corresponds to a word accepted by the automaton, estimating the number of words will tell you for how long your model checker will run, and so this is a sharp NFA problem. Now, when do we want to count traces? Well, if your programs are concurrent programs, so you have different threads and stuff that can execute in parallel, and it doesn't really matter in which order this happens, then this is the same as having some symbols in your words that will be allowed, that can be swapped. And now if you have a smart model checker that does some kind of partial order reduction, then this model checker can be much faster by enumerating one word per class. One word per trace. So this is a trace counting problem here. Good, so that was for the motivation. Now how hard are these problems? Well, pretty hard, actually. So sharp NFA, counting words, this is Sharpie complete. So this class Sharpie, it's a class of counting problems. It's basically it's pretty hard. We don't expect this to be tractable at all. It's as hard as counting solution to a SAT problem. Just to give you an idea, if you have a sharp hierarchical, every problem in the polynomial hierarchy you can solve in polytime. So that gives you an idea of the power of this thing. Now, as I mentioned before, counting traces is an extension of counting words. So yeah, this other problem is sharply hard also. But in a sense, it's harder than just counting words. And I can try to explain it like, by looking at a fragment of the problem. If my automaton is deterministic, counting words is very easy. You just have to count the passes of a given length that go from initial start state to accepting state. That's sharp DFA, D for deterministic. You do this in linear time with dynamic programming. Okay, cool. Now, if you try to count traces, it's become sharply hard already, even if you have a deterministic automaton. So my interpretation of this is that by deciding to count equivalence classes, you add some kind of source of non-determinism that already makes the problem hard. And when you add this to the existing non-deterministic structure to the NFA, you can imagine what kind of amusing cocktail this gives you. So that's hard, but there is some good news. And the good news is that if you want to solve it, if you relax the problem and only tries to solve it approximately, then you can do it in polytime in some sense. So so they are what's called FPRAS, fully polynomial time randomized approximation scheme. You can replace scheme by algorithm. So it was known already that counting words admits an FPRAS. So that's an algorithm. You give it an NFA, the automaton, you give it the word length, and you give it two parameters, epsilon and delta. They are typically very small, but never zero. And the algorithm is probabilistic. It will do a bunch of coin tosses, and so it will return a random variable, but with high probability, this random variable will be very close to what you actually want to compute. In this case, the number of words of length n accepted. And the most important thing, this algorithm runs in polytime. So that's an FPRAS. And it was an open problem for a long time of whether there is an FPRAS for counting words of the automaton. And a few years ago, it was shown that, yes, there is an FPRAS. So the exact problem is hard. The approximate problem, you can do it in polytime with randomization. And the question we ask in the paper is there also an FPRAS for counting traces? And the answer is yes. So that's basically the main result. And now I will try to spend the last of the talk describing a bit how the FPRAS works. But now, to do that, I have to explain how the FPRAS works for counting words, because the algorithm for counting traces is very much based on the algorithm for counting words. Here there are several algorithms you could start from. So the first one, as I said, it was obtained by Arenas, Krugvel, Jarayam, Riveros in 2019. But it has been improved since then. So my two collaborators and one of their colleagues, they obtained a faster algorithm 2 years ago. And I myself, with Kuldeep, we obtained yet another faster algorithm last year. And this is this algorithm that we have been improving for counting traces. Now, I will first go through the FPRAS for counting words, and then I will explain what are the extensions for how do you need to modify it to count traces. The good thing is that all these algorithms, they all share a very simple structure that you can summarize in these 6 lines. And I will go through these. So the first step is always the same. You enroll your FPRAS. Since you're only interested in words of length n, you start from this cyclic FPRAS, and you enroll your automaton. You start from this cyclic automaton, and you enroll it to an acyclic automaton that only accepts the word of length n, the word that you want to count. To do that, every state will be cloned n+1 time at most, and you obtain this nice layered structure. So the reason we do this is that we have an inductive procedure that will go through every state, through every layer, and through every state of every layer one by one. And for every state, it's going to compute a bunch of random variables. So this L, this superscript L, means that you are at layer number L. Okay? So starting from the initial layer, we compute the following. We have sets of samples. These are random sets. Samples, in this case, are words that are accepted by the state. We have polynomially sets of samples, and each set of samples has a random size, but we can show that they will stay small, basically. And this set of samples we use to compute an estimate of the word count at every state. That's this NQL. That's the estimate for the word count for QL. And we do this so that this NQL is a tight approximation of the actual size of the language for this state QL with high probability. So not only are we solving this sharp NFA problem for the very last state, which is what we really want at the end, we are solving it for every intermediate state. And all of this is like, each state is using the result from the previous state to do the computation. And the main computation is just a union of sets problem. So if you have a state QL+1 at layer L+1, you have already processed its children at layer L, you already know approximation of the language size, you have a bunch of samples, and well, the language of LQL+1 you obtain by doing a union of sets, and you append the transition letter. In this case, it's A on all transition to simplify. Now, the problem is that these sets are not, their intersection is not necessarily empty, and that's already sharply hard to do, to compute exactly the size of the union of set. So, but we know, fortunately, it's been years since we have found a way of doing this approximately. If you can approximate the size of the input sets, and if you can sample uniformly at random and independently from the input sets, then you can approximate the size of the union set. So we keep doing this for every state as we go through the unrolled automaton. Now, so the name exactly of the procedure that does this is a median of mean estimator. So people who eat randomized algorithm for breakfast will know this, but I won't go through that. I will rather explain how the sets of samples are constructed, because that's the part where we have to modify when counting traces. So it depends on which SPRs you're considering, but so for the one that we use the one with the easiest sample construction possible, where we say, okay, we have samples for the children of the state, and we want samples for the state for the new state QL+1. Well, that's easy. First, we take all the samples for the first child, and we extend them. We append A at the end, and that's it. We have words accepted by QL+1. Good, now we look at the second child. We take all the samples, we append A at the end. We obtain, again, words accepted by QL+1, but we are going to remove everything that could have been accepted by the first child, because we don't want to favor a word rather than another. If a word can be derived in many ways, as many accept in a run, but some other has just one or two accept in runs, we want both of them to be sampled with the same probability. Uniform sampling is important to do the approximation. So that's, yeah, so we have to do this membership test to remove everything that could have gone through the first child. And same for the third child. We take all the samples, extend them with the transition letter, and remove everything that could have been accepted through one of the first two. So one of the problems of this approach is that it makes samples dependent of one another for a reason I will not explain, and that's kind of a challenge for the estimator. But we deal with that issue in the paper where we describe this algorithm for counting words. Now, for counting traces, what's the changes? Well, luckily it's the same overall structure, the same 6 lines. But now the random variables do not exactly mean the same thing as before. The estimate is an estimate on the number of traces, not a number of words. The samples are still words from the language, but now we have to make sure we don't have 2 words for the same trace. So we want at most 1 word per trace. That's what we call a canonical representative. So these are the sample set. And it means the sample construction is becoming harder. It's still the same idea as before, but now, so okay, so the samples from the first, oh, actually there is a typo here. Never mind. No, there is no typo. The samples from the first child, we take them all, we extend them by A. Okay, cool. This gives us different canonical representative for different traces. Now, samples for the second child, we extend them by their letter, and then not only do we remove everything that could have been accepted by the first child, but we also remove everything that has an equivalent word that could have been accepted by the first child. So it's much harder. We have to do a membership predictive test every time to get rid of a lot more samples that could have been created through the second child, and same for the third child, and so on and so forth. So luckily, this membership predictive test we can do in polynomial time, kind of. Now, the second real hurdle that we have to overcome is where this talk could become a lot more complicated, but I will keep it in one slide. So that's always a problem. We need to go deep into the analysis to realize that there is something annoying going on. So because we create samples that are dependent of each other, we cannot use all the shiny tools from randomized algorithm analysis or the churn of bound and all. We have to go back to the old tools, Chebyshev inequality and so on, and we need to bound variances. Our estimator that counts how many traces is going to be centered around the correct value, but the variance has to be bounded to know that it's not going to wander around too far from what we really want. And bounding the variance kind of means that we have to understand when are the samples going to be really dependent of each other. When exactly is the probability to sample simultaneously two words going to be a lot more than the probability of sampling them if they were independent. And for a reason I'm going to swap under the rug, this leads us to answer the following, to look at the following problem. If I give you two languages and you know the number of their traces, T1, T2, I want to know how many traces will be in their Cartesian product. If we were talking about words, it would be very easy. You just take the product, that's it, done. It's not true for traces anymore. All we could use is this lower bound where we have to use some parameters called the width of this alphabet with independence relation. And using that and plugging this into the analysis, adapting everything, we could get good bounds on the variance and make the analysis go through. And the result is this algorithm, this FPRAS, for counting traces on a non-deterministic finite automaton. And that's it. I'm not going to talk about the uniform sampling. It's a shame because there are a lot of cute ideas in there also. But I invite you to read the paper if you're interested. Thank you.
Thank you for the talk. I think you mentioned that if the independent set is trivial, then the problem is very easy. Yeah. But I can imagine that if the independent set is also like all pairs, then maybe the problem is also very easy as well.
The problem yeah, is that correct?
My question is, is it possible to get a runtime that is dependent on sort of a metric on the size of the independent set?
Yes, so that's, yeah, so you almost caught me here. So that's the metric you're referring to. The width of the concurrent alphabet, so it's dependent on the independent set. So to be exact, this pair, sigma I, is kind of fixed before the problem because you will have this n to the gamma that is part of the complexity. So the FPRAS is only polynomial time when you fix these two guys or when you bound the size of this gamma. And for the case, when the independence relation is empty, gamma is either 0 or 1, and I think it's only 1 if the independence relation is everything. Yes, sounds true. So that's the metric you're suggesting.
Time for one more question. Can you also show us the exact complexity of the algorithm? Do you have that expression?
You're going to ask a question on your own paper? I don't know the exact complexity by heart.
So can you say something about the size of the sets that you build through sampling and how that depends on the parameters of your problem?
The size of the sample sets?
Yeah.
So they are random variables as well, but we keep them polynomial and sorry, here. Like there is one line that I've not written here. When the sample set becomes too large, we just stop the algorithm and we return some garbage. But we prove that it never really happens and that it's going to be, the size of the sample set is going to be quadratic, but okay, it will be quadratic for words. Yeah, quadratic for words, I think, but you will have this gamma that will pop up in the side, but also in this case. I have to look up the exact value, but yeah.
Thanks.
Okay, so let's thank the speaker. Next up, we have Fauzi Atik. Fauzi is going to talk about parameterized verification of Intel x86 programs.
Okay, thanks. This is a joint work with Parosh, Ahmed, Kumar, and Prakash. And in this work, I will talk about parameterized verification of model of Intel x86 programs. So I will start first by a brief introduction of Intel x86 programs, and then I will try to explain what's a parameterized verification, and then finally our results. First, x86 programs. Usually when they program concurrent and parallel program, they assume that this sequential consistency or the strongest consistency model, where we have processes or threads that are writing to the memory, and this write or read are done in atomic manner, and all the execution of all these processes or threads are interleaving with each other. This is a very simple model and intuitive, but it disallows many optimization of the hardware and compiler. In fact, modern processor or compiler, they allow some reordering of instruction, and also they use some cache and store buffer for efficiency reasons. And this has led to the introduction of the weak mirror models framework, and this framework captures the semantic of such execution. An example of this is that we have a write here, is followed by a read, and they are both issued by the same process. And now what can happen that this read will be executed before this writes. And this is what we call write-read reordering. And this is one of the reordering that is happening in the total store ordering, which is, let's say, the formal model for x86 processor. And this talk will be about TSO. And this model has been formalized in this seminal papers by Scott, Owens, Smith, Sarkar, and Peter Sewell in 2009 and 2010. And the model is, it has some, we have as usual some processes, some shared memory, but we put in between this processor and shared memory now a store buffer per process. And this is a FIFO queue, you can see it. So how it works, let's see an example how it works, and it will be brief. So here we have only one process, P1 will issue some sequence of instruction. And first, the first process, process P1 will write set x to 1. Instead of updating directly to the memory and rewriting the value of x to 1 from 0 here, then what would happen that this x will be added to the store buffer. It has no immediate effect on the shared memory. It's only visible for the process P1. It's still not yet visible for process P2. And then this process will issue another write. He will or she will set x to 2, and this will be added again to the buffer in some FIFO manners. And now, if this thread would like to read, and this is a combined read and test for just for explanation and to make it easy. And here, this thread would like to read that the value of x is equal to 2. What happened that this thread will first check its own buffer and see if there is some pending write on that variable. And if yes, it will get the value of the last written value write operation on that variable. And here we see that the last written value on x is 2, and this is exactly match this read and test operation, and therefore we can execute this operation. The same for the last instruction for y. We'd like to read that the value of y is equal to 0, and in this case, the process P1 will check its own buffer and see there is no pending write on the variable y, and therefore it can fetch its value directly from the memory. And you see in this case that this read operation has overtaken all this pending write operation. They have not yet reached the memory, and then it got its value from the memory. So this is why we are saying that read overtake writes. This is a very simple model and intuitive, but it does not capture somehow all the write operation of Intel. And then, of course, at the non-deterministic manner, this writes will be updated to the memory. First, we set x to 1 and x to 2. And recently, there is another paper which extends this TSO model with other types of memory operation and also non-temporal store. And this is captured, let's say, in faithful manner what is exactly happening in Intel x86. So we'll have different types of writes, and here in this talk, I will only focus on two, this write back memory operation and non-temporal writes. And then I will use WB for the write back and NTW for non-temporal writes. There are other memory operations like write combined, write through, and store fence, and other ones. But to make this talk concise, I will only focus on these two types of write operation. And we have, as usual, a buffer. Now, as you can see that I have used different color, but also I have used subscribe to differentiate between them. We have this write back now operation, and this is like the previous TSO writes exactly. It behaves in the same manner. And we have this NTW writes, and this is like the PSO writes, which is standing for the partial store ordering memory models, which is much more weaker than TSO. So let's say again an example, a simple one. So the first instruction of the first process is just issuing NTW write. It's setting y to 1 here. And as in the classical TSO model, this write will be added to the buffer. So we'll add this y is equal to 1 to the buffer of P1. Then P2 will write set x to 2 using write back operation. And this will be added to the buffer of P2. Now, this is the difference between classical TSO and extended TSO, what we call ETSO here, that, for example, this NTW write, now it's not anymore FIFO queue, how we update the memory. It's not the first in, first out. But rather this one, this NTW, which is setting y to 1, now can overtake any other write on different variable. So in some sense, this is why setting y to 1 can go and update the memory immediately. Another different behavior that, for example, this write back here cannot overtake other write back like in TSO, classical TSO, but it can overtake NTW writes on different variable. This means that setting y to 2, this write here can overtake this write on X and go and update the memory also. And for read operation, it's the same as the classical TSO, but we first, for this process P1 will check its own buffer and fetch for the value from the last written write on that variable, and here it's 2. And for reading y, there is no pending write on its own buffer, and therefore it will fetch the value from the memory. And to summarize extended TSO, as I said, NTW can overtake any other write on different variables, and WB writes can only overtake NTW writes on different variables. And as you expect, this leads to extra behavior and potentially bad ones. For example, if you run Decker protocol, for example, on TSO or extended TSO, the mutual exclusion property will not be satisfied, and you can end up in that two processors or two threads will be running their critical section at the same time. I don't have time to go through this example, but believe me, this could happen. So what we know about this classical TSO and extended TSO as results? Well, so what we know that for the classical TSO, when we have, let's say, finite number of processes running in parallel, that the problem is decidable, but it's highly complex. It has a complexity which is non-primitive recursive. And the proof has been done by reduction from to an extended class of lossy channel systems. And then for extended TSO, it has been shown when you start mixing this NTW and WB writes, using different types of writes, then the problem, the reachability problem will become undecidable. So, and then in that paper, the idea for which under-approximation, meaningful under-approximation, that we can regain decidability. And one idea that we say that for each process will be allowed only to alternate between WB and NTW. So let's see concretely an example. We have here some sequence of instruction, and we can focus only on process P1, and we can see here, we can divide this sequence of instruction for P1 into different stages. And the first stage, we can see that this process will only perform WB. The second stage, this process will perform only NTW. And the last one, this process will perform WB. This means that in this execution, for the process P1, the process P1 will perform 2 alternation, and this is equivalent to 3 stages. So if we are giving some K, and we bound the number of possible alternation per process, then the reachability problem will be, again, be decidable. And this has been done by reduction to some the partial order store ordering, which is a weaker model than TSO. So now back to the first slides, and as the title is saying that we have parameterized verification of Intel x86, and I have tried to explain what this Intel x86 program, semantic, and now what I mean by parameterized verification. Parameterized verification is trying to solve this reachability problem when we have unbounded number of processes running in parallel, and they are running identical code. And they are identical code. So we don't know how many will be running in parallel and a priori, and we would like to verify that, for example, if we have mutual exclusion protocol, that at any time there is only one process running its critical section. So this is what parameterized verification means. So now, what we know about results about parameterized verification. Under the sequential consistency, we know that this problem for finite processes, that this problem is X-space complete from 92, and this is a well-known result. And in Javier, Pierre, Ganti, and Drupak have worked a lot on this problem when we have no locking and no compare and swap or no test and set, and they showed that the complexity goes down, and to be we can solve the parameterized verification in polynomial time. So this is what we know under SC. Now for this, we studied this parameterized verification for this extended TSO, and our results are the following. First, we showed that parameterized verification is undecidable in general, and this is by easy reduction from the finite case, because we have this compare and swap operation, and therefore we can use this compare and swap operation to select a finitely many processes to be active, and we make all the other ones idle. And therefore we can have a reduction from the reachability problem for in the case of bounded number of processes. Now, we have shown that if we use the same under-approximation, which is bounding the number of alternation between the different types of writes per process, then the problem will become decidable. And here you observe that we are bounding per process, so the number of all possible alternation for all possible process is unbounded. So, and this will be the rest of the talk. So I will try to give you a brief idea. So what are the challenges in addressing this? So we have this extended TSO. Now we have unbounded number of processes running in parallel. We don't know how many. And then we have FIFO, we have buffers, which are also unbounded. And plus we have possible reordering between all this instruction between NTW and WB writes. So we have many challenges to address. And the question how we could solve this, we have 3 dimensions of, let's say, unboundedness here. So, and our approach is just to use this framework of well-structured transition system, which has been introduced in the 19th by Parosh Abdullah, Ben Johnson, Alan Finkel, and Philip Schnobelen. And this framework is some uniformed way to allow you to show the decidability of reachability. And in order to apply this framework, you need to define a will quasi-order, which is a quasi-order for which you can see it as you have infinite sequence of configuration, and for any, there will be always some index I and j such that I is smaller than j, and then the configuration Cj is smaller than Cj. And then you need to have another ingredient, also monotonicity of your system. And monotonicity means that if you are in some configuration C1, which is smaller than C2, and you know that from C1 you can move to configuration C3, then monotonicity implies that there exists some configuration C4, which is larger than C3, and also it's reachable from C2. It's some kind of simulation. This means that larger configuration could simulate any run of smaller configuration implicitly. So if you have these two ingredients and many others, like disability of checking this ordering between two configurations, computing the set of predecessor, then you can deduce the reachability problem for such a system. Now, I would like to apply this. And it's not straightforward to apply for extended TSO. Because we have buffer and we'd like to define a will quasi-order on buffer. And what we know as will quasi-order for words, because you can see the buffer as a sequence of words, is the subword ordering. And the subword ordering means that you lose some element of the word and you obtain the other one. For example, here, if you remove or delete y is equal to 1, you obtain exactly the smaller configuration. But this does not preserve monotonicity for TSO. And therefore, would like, because here for the larger configuration, it cannot read that the last value of y is equal to 2, while the smaller one can do it. And therefore, the larger configuration cannot simulate the smaller configuration. So, and the question how to define an ordering that allows us to show the suitability of this parameterized verification. So what we do here in this paper that we introduce a new model, which is equivalent to the extended TSO under the assumption of bounded alternation. And this model, we call it NTW load. And this is a, let's say, non-trivial extension, which is DLTSO, or load buffer semantic of TSO, that has been introduced in 2016. And then once we have defined this new equivalent semantic of extended TSO, we will be able to apply this will-selected transition system with some more complicated will quasi-order still. I will talk briefly on it at the end of my talk. But first, let's briefly go through this DLTSO, what does it mean, and this is for the classical TSO. DLTSO, you can see that TSO is just that putting writes in the buffer and delaying their execution so that reads can overtake them and go to fetch the value from the memory directly. But DLTSO takes the DL view of it. Instead of delaying the execution of writes, it will allow the writes to go directly to the memory. But it will use some load buffer here to store somehow the history of the memory so that reads can go here and fetch previous value or snapshot of the memory. So let's see an example. Here, the process here will do a write operation. Now, instead of storing it in the buffer, it will update directly the memory. And here we set x to 1, and at the same time, we add 2 snapshots to the load buffer of all the processes. And we mark here, you can see here, I have used some marker to say that this snapshot for the variable x, it has been done by this process. Because always we need to do this last written value. If it's still in the buffer, then the process needs to read the last written value. For the other one, we don't have this marker because this write has not been done by this process. And also, you see that we keep all the history of the memory, but some of them are not relevant at all. This process P1 does not need or see this memory snapshot. And therefore, we allow that this memory snapshot to be deleted in a non-deterministic manner. And this will allow us to have this well quasi-order. And for reads, we check first our own load buffer. If there is some own written value, then we need to read that one as this read own write for classical TSO. Otherwise, we go to the oldest message in our load buffer, and here this is the oldest message in our load buffer, and the value of y is equal to 0, which is matching our read operation, and we validate it. So it's another view of classical TSO, or it's the DL view. So, and then this is equivalent to the classical TSO. And the question how to extend it now to this extended TSO under this assumption, keep in mind this assumption of bounded alternation. So we have bounded alternation, you remember. So here, if I see this code of the process P1, we have here does some writes here first, and then NTW. But you see that this write setting y to 4, it can be executed, it can overtake all the other writes because they are on different variables. In some sense, we'd like to allow that this writes to be executed before all the others. And this means that we need to execute this part of code before the other one. And how we do it, we just guess where this each stage, which stage is WB, which stage is NTW. And then in order to allow some reordering between all these different writes, we run them in parallel now. So in some sense, we replace this process P1 by sub-processes. So we have here, since we have 2 stages, we will have 2 sub-processes that are running in parallel, that they have each own load buffer. And if you take the concatenation of these 2 load buffer, you obtain the load buffer of the whole process P1. So, and you see that this stage 1 ends when stage 2 begin. And then also we have here, for the NTW stage, we have, let's say, like PSO buffer, one buffer per variable, what we call NTW buffer. This is because NTW can be reordered with respect to each other, and therefore we have introduce one buffer per variable here to reorder them. But this is not enough, because, for example, you see here, this NTW on X cannot overtake all the write back on X for the first stage. So there is some kind of causality between these stages. We cannot allow anything. And therefore, we need to add some component to maintain this causality. And one of them, for example, stage 1 will speculate, for example, on what will be the last written value. And we say that stage 1 will write set x to 2 at the end of that stage, and will not do any write on the variable y. And we need to validate such a speculation or a guess. Now let's see. Stage 1 will start doing writing setting x to 1. And we are using this load buffer semantic. It will immediately visible in the shared memory, and we'll have a snapshot which will be added to the active buffer, load buffer, which is this one now. Now, as I said, that this is sub-processes, and they can run in parallel. And therefore, stage 2 can run in parallel, and then we can read the value of x is equal to 2. And then we do the NTW, which is writing NTW and setting it to 3, and then we add it to this small buffer that we have here. And then we do the next operation, and then we can see here, these 2 can go to the main memory in any order, and we can reorder them. But we cannot, this write on X cannot go to the memory because we have not validated our guess, and then we are blocked here for the variable X. But the variable Y can update the memory and add snapshot to this one. And this will become the active load buffer and not this one anymore. And then stage 1 can continue, set X to 2, but you see now this is our active load buffer. All the snapshot will be added here. And then we can validate now our guess. We have set X to 2, and we remove this constraint now. And then we can read Y, and we read it from our own load buffer, and then the second stage also read X. And then since he has a pending write here, it will read from it. And then finally, this pending write now can go to the memory, update the snapshot, and update the second process. This is the main idea. So we use now will quasi-order, but we are using a subclass of it, which is called better will quasi-order, and this is the first time has been used to show new decidability result. And this is enjoy much more stronger closure property, because we need to make sure that all the process, because we have unbounded number, all of them will validate their own speculation or guess. So in summary, we studied this parameterized verification under ETSO. We showed undecidability, and we showed decidability under this restriction of bounded alternation. Future direction of work is include persistency of extended TSO, and also looking to parameterized verification with one leader or without compare and swap or read and write compare and swap operation. So thank you.
We can have one quick question. Okay, so I think in the interest of time, we'll move to the next speaker. So the next up is